Good morning. The lecture of today is about the sustainable production of the membranes. You know, in recent years, the environmental aspect of any fabrication is very important. And we must go to a green technology for production of any products. In the fabrication of membranes, we also select green polymers, green solvents, and generally green methods for fabrication of membranes. The application of the membranes, as before say, that no high environmental problems, because the separation is a physical separation, and we very low use the chemicals, and therefore only the consumption of energy is important in membrane processing, and we try to reduce the energy consumption, because for producing of the electricity and energy, the carbon dioxide emission can be pollute the air and the world. But the main problem in the membrane fabrication is solvents. Because, as discussed, for fabrication of membranes, we first usually dissolve the polymer in a solvent and prepare a casting solution. And after casting this solution as a sheet or as a hollow fiber, as a tube, we want to separate the phase. And in this case, we use non-solvent induced, vapor induced, thermal induced, and others process for fabrication of membrane. And in this case, we must remove solvent from the membrane. And 80%, normally 80% of the casting solution is solvent. And after fabrication of membrane, this solvent should be managed. And this solvent is usually toxic and cause environmental problems. Therefore, in development of greener and sustainable membranes, we mostly focus on change of the traditional solvents with greener one. The second problem is the polymer, but the environmental aspect of polymer is very lower than the solvent, because the use of polymers is not very dangerous, and we can replace them with biopolymers if we have find the biopolymer with the properties near the usual and conventional polymers. There are strategies for fabrication of green membranes that you see. That one is the greener solvent for casting, coating, cross-linking, and interfacial polymerization. In all processes of membrane fabrication, we have the main part of our solution is solvent, and we must use a greener one with low toxicity, low volatility, when the solvent can be vaporized and go to the atmosphere, can cause to the environmental problems. We can reduce the waste minimizing step. In the production step, for example, with the reducing of the batch size, we can reduce the consumption of solvents, okay? Or we can minimize energy consumption with use of the novel and new pumps that use very, very low energy. We can reduce the energy consumption in the membrane fabrication. In the membrane fabrication industrial, we usually have some motors for rolling and some pumps for pumping of the liquids. And we have no energy consumption, but if we can reduce this energy consumption, we also we can reduce the environmental problem. Therefore, in membrane fabrication, we must speak about change of traditional polymer with biopolymers, and the most important, change of the green, change of traditional solvent with greener one. As investigated by this team, Drioli in Italy, with all of the membrane production factories, most of companies, about 70%, treat the produced wastewater. When we have a NIPS method, in the NIPS method, solvent go to the water bath during the coagulation bath, during the phase inversion, and we have a lot amount of water-based wastewater that have solvents. This solvent is also expensive. Some companies recover this solvent and reuse again, especially hexane, because hexane is a low boiling point. They usually distill the wastewater and separate the hexane. But separation of dematch NMP is very hard, and in some cases, without any treatment, drain the wastewater into the river, sea, and other places. The most used solvents is THF, NMB, DMF, dematch, and we must replace with greener one. There are different types of greener solvents, and the most famous is water. Water is no dangerous solvent, and if we can use water instead of DMF and NP, it will be very good, very, very good. But we know that the carbon-based polymers do not dissolve in water, and water is a non-solvent, not solvent. But there are some membranes can be used water for fabrication that I will discuss. In the case of the definition of the green solvent, we say that a green solvent is low toxic, low volatile, low flammable. The flammable can be dangerous in some cases. Renewable, that means have bio-based green solvent. Biodegradable, if we have a solvent that can be biodegraded with microorganisms, after the application, we can treat the wastewater. But many of solvents are toxic for microorganisms, and we cannot use bio-based or biology for treatment of wastewater. As you know, we have 12 principles of green chemistry for reducing of the environmental problems. And you see that three of these principles is related to the reducing of the toxic solvents and use of biosolvent or green solvent. Therefore, we see that the replacement of traditional solvents with green solvent is very important. Some companies in the world categorize the solvents based on the greener behavior and suggest some solvents can be replaced with the toxic. For example, these companies produce these tables and says that, for example, methanol with these properties can be dangerous in this area or low dangerous in this area. And we have many companies discuss about, and we can, having of these tables, we can select that which solvent have low toxicity, and we can replace with our solvents. This table of these companies that shows that, for example, this butanediol from the flammability is a bad, but from the waste is the average. Therefore, give numbers for these solvents, and based on the process and the application from healthy, flammability, environmental impact, we can select the lower toxic solvents. Generally, when we see these tables, we can categorize the solvents as a very hazardous, highly hazardous, and when go to the right, the hazard is reduced, and this solvents is good green solvents. For example, when we have this table in the membrane fabrication, we use that our used solvents in the membrane fabrication is located here, DMAC, DMF, NMP. It's hazardous, okay? Chloroform is very hazardous. But in the membrane fabrication, we use DMSO. You see, dimethyl sulfoxide is also a solvent used in membrane fabrication and can be replaced DMAC with DMSO. Okay? When we go to the right, the toxicity is reduced. If we can prepare a membrane with DMSO, we must use DMSO because DMSO is greener one, and go to the right. Or toluene. Toluene is better than THF if we can use toluene. Therefore, with going to the right, the toxicity is reduced, and you see this table is water and alcohols. Okay, most alcohols. Therefore, if we can use ethanol instead of, for example, methanol, methanol have low toxicity. If we can use ethanol, we must use ethanol, not methanol, because methanol have some problematic issues. Therefore, with this table, we can find a green solvents that we can replace with toxic ones. This is the usual polymers, and we must replace these usual polymers with biopolymers. Cellulose acetate is a bio one because fabricated from cellulose. During this traditional polymers, the cellulose acetate is green one. But others are synthetic polymers, and synthetic polymers have environmental problems. And these are the used traditional solvent in fabrication of membranes, and we see that DMSO can be categorized in this green. And if we can, for example, prepare cellulose acetate with DMSO, we have a good green membrane. But we have a big problems, and the first big problem that our selected solvent can be dissolved the polymer. First step of membrane fabrication is dissolving of a polymer in a solvent. First, the selected green solvent should dissolve the polymers. And in many cases, the good green solvents do not dissolve. For prediction of that our selected green solvent can be dissolved the polymers, we have some software and some calculation for prediction. One of them is Hansen solubility parameter for prediction of polymer. When we have a new polymer, new biopolymer, we want that this new biopolymer can be dissolved in new green solvent, and we have not in the literature that use this green solvents. We must first calculate that from thermodynamically view, it is possible that this solvent can dissolve these polymers. In the Hansen solubility parameters, we first calculate the RA with this equation. We have three soluble parameters, three different soluble parameters. One, D, is dispersion, dispersivity. Second is polarity, and third is hydrogen bonding ability. Okay? In the dissolving of a polymer in a solvent, first the solvent should adsorb, should interact with polymer for attachment, and the next diffuse inside of the polymers and separate the chains. The solubility, it means we separate the salts from together or the polymer chains from together. Therefore, for solubility of a polymer, first the solvent should be adsorbed, should be interact, go to the polymer body, and begin to separate the chains together for easy movement. When we have a soluble, we have a solution, we have a easily movement, but in the solid phase, we have not good movement. Okay? Solubility is mean the easily movement of the change. For interaction of a solvent and a polymer, we must have good functional groups. We know that the polar solvent can dissolve polar components. Nonpolar dissolve nonpolar, okay? Therefore, polarity is important and hydrogen bonding is important for interaction, okay? We must have an interaction and the parameter shows this interaction. One is polar, polar can dissolve polar, nonpolar can dissolve nonpolar. Therefore, when we have a polar polymer, such as chains in the solution, therefore we can calculate or show the ability of the solvent for dissolving. One is the solvent solubility, dispersion, solubility properties of the solvent polymer. We calculate this RA, obtain a number, an amount, okay? And we have the solubility, we have this RA0 is solventation radius. R is radius. Solventation radius of an polymer. For example, for polysulfone, PVDF, we have this number, okay? We have this number for polymer, for example, is 10. We calculate RA for our solvent and PVDF. If we obtain 12, this 10, DMSO, NMP, in the handbooks, in the tables. For polymer also, okay? But you synthesize a new solvent. And you check the handbooks and you do not find. In this case, we can calculate these sigmas with this equation and with this functional group. There are, you see, for example, in this FD1, and with base of the structure, we draw the structure of a solvent, and based on the structure, we can calculate these amounts and the next use in the Hansen solubility parameters. Every functional groups have a specific amount, and with using of this amount in these equations, we can calculate the Hansen solubility parameter. V is the volume, molar volume of the groups, and this F is the located the amounts here. Therefore, if we have a new solvent that no data in the literature, with using of these equations, we can calculate the sigmas and go back to this equation. We calculate the RA and the R0, and we can predict that this solvent can dissolve or not. For obtaining, if we have a new biopolymer, for the first time we synthesized a new biopolymer, our new polymer, we need to calculate also R0. For famous polymers, there is R0 result in the literature, but for new polymers, there is an equation. We must use 22 solvents for dissolving this polymer. And we say that this polymer, we select 22 solvents. We say that our polymer dissolve in chloroform very high, 2+, in DMAC good plus, in the water no minus. We have a table plus, 2+, minus, and based on this 22 solvent, we can calculate this RA0. Now we go to the examples. If any question about Hansen solubility and as a high green solvent, the water is the best one. If we can prepare the membranes with water, it is better. But we know that the water is very polar and only can dissolve the hydrophilic, very, very hydrophilic polymers. Therefore, only these polymers can be used in fabrication of membranes with water as a solvent. You see that the famous one is PVA, and this right is the natural polymers, biopolymers. And if we prepare, for example, chitosan membranes, both polymer is green and solvent is green and is very good. But most of these polymers, when is soluble in water, during the using of membranes, the water can be dissolved the membrane. And after 2 days, the membrane will be destroyed. Therefore, for removing of the solubility, we must change thermoplastic polymer to thermoset. We have 2 types of polymer, thermoplastic, thermoset. Thermoplastic can be dissolved in solvent, thermoset cannot. Thermoset, that means we have a cross-linking between the chains. Solvents go for separate, but cross-links do not permit. Therefore, in the fabrication of the water-soluble membranes, we must use cross-linking agent for removing of the solubility. Therefore, in this all of mixture of in these solvents, water and these polymers, we add the third section, mostly glutaraldehyde as a cross-linker, that during the curing of membrane, during the cross-linking, the solubility of the membranes will be removed. So PVA, previously we discussed, PVA membranes can be used in pervaporation. In pervaporation, we say that if we want to separate water, low amount of water, from an organic solvent, we use PVA, and the membrane type is non-porous. Therefore, the fabrication of the pervaporation membrane with PVA is easy, and there are commercial PVA pervaporation modules that is very green, and we have a water solvent. For grafting of these groups on the membrane surface, we also can dissolve these polymers in water and use for grafting. Or we can fabricate the membranes with chitosan, xanthan gum, dextran, and carboxymethylcellulose. CMC is carboxymethylcellulose for production of the membranes. Both porous and non-porous membranes can be prepared. In this case, we have not used water as non-solvent, because here we have a water as a solvent. Therefore, for example, for production of the non-porous membrane, we used WIPS method. We dissolved the PVA in water, add cross-linker, coat on the glass, and with heating, we remove the water. And when water go to the atmosphere, we have no problems. But in the traditional solvents, when the acetone go to the weather, cause to the ozone layer problems and others. With additional poroformer, we can porous this layer with addition of poroformer. As discussed in membrane distillation, we say that we have a low critical solution temperature. That means in high temperature, polymer is dissolved, and when reduce the temperature, polymer is insoluble. High temperature soluble with reducing, and we say that it's thermal induced method, TIPS. In the TIPS, in high temperature, we dissolve the polymer. With reducing of temperature, solubility is removed and phase inversion happens. In this example published in this paper, used the polymer, you see that can dissolve in the low temperature, and with increasing of the temperature and evaporation, we have a membrane, and next, by reducing and solidification for removal of the membrane, we can cause it in the water bath. Therefore, there are many different techniques for fabrication of the membranes with water as a solvent. Or we have a polyelectrolyte. The soluble polymers in water is named polyelectrolyte, the soluble polymer. Polyelectrolyte or polyelectrolyte are soluble polymers in water that can be cationic or anionic based on the functional group. With change of the pH, you see here, we want prepare a membranes from water-soluble polymers. Polyelectrolytes are soluble in water. Okay? For fabricating of the membranes from polyelectrolyte, we mix two polymers, one with negative charge and one with positive charge. Okay? We dissolve the polyelectrolyte. This polyelectrolyte mostly used in coagulation process in the water treatment for increasing the precipitation of the iron or aluminum in the coagulation bath in wastewater. We add one positive polyelectrolyte and one negative polyelectrolyte. And we have a solution. But by change of the pH, we reach to a point that the amount of negative and positive charge is equal in a special pH. In this case, we have this arrangement. The negative charge contact the positive charge. Okay? Understand me? And when reach together, contact together, and the solubility removes and precipitate. And phase inversion happen. Phase inversion is the separation of the solid from the liquid. With a specific pH, the positive and negative charge connect, attach together, and precipitate. And for example, in this case, in high pH, we have a soluble polymers. In a low pH, we have a not soluble polymers. and we can prepare porous membranes from the polyelectrolyte and from the water as a solvent. This is a very good technique for fabrication of polymeric membranes with use of water as a solvent. And fabricated, you see the high porous membranes with this technique. After water, if we can use bio-based solvents, is very good because we produce this biosource from the bio-based, from fats or oils, or from the herbals, okay? Therefore, if we can produce these solvents from the biomass or from the fats and oils, the toxicity of this solvent is very low and biodegradable, and after use, the release to the environment is not a problem. There are different categories. The famous one in the membrane fabrication, this is one. Some examples. The famous bio-based solvent is ethanol. Ethanol produced from sugar. And therefore, it is very, very green and no problem of use. Therefore, but ethanol, such as water, is a polar and hydrophilic solvent and can only dissolve the soluble, the hydrophilic polymers. Some polyurethane, some polyvinyl butyral, PVA, polyethylene glycol can be dissolved in ethanol, and we can use ethanol for fabrication of these membranes as a nanofiber or as a flat sheet and others. PEBOX is a famous polymer in the fabrication of gas separation membranes, and more than 30 or 40 years is used for the fabrication of commercial carbon dioxide separation membranes, and the solvent of PEBOX is ethanol. And industrial scale, ethanol is used for the PEBOX dissolving for fabrication of RO membrane. The bio-based solvent is silane also. Silane, this is an NMP, traditional one. This is the structure of the silane. And you see that there are some similarity between them. And in most cases, silane is used instead of NMP. And see that with use of the silane and control of conditions, we can dissolve PVDF and polyethyl sulfate, and the good membranes have been fabricated. I have some studies about use of green solvents in the membrane fabrication. The membrane is good, the flux good, but the stability is low. In the papers, maybe do not mention, because everybody wants to say that our membrane is good, but our results show that when we use bio-based, for example, this silane, the resulted membrane have 50% lower tensile. The membrane prepared for NMP is very stable, no tear, but the membrane fabricated with silane, with applying stretch, it tears very easily. Therefore, the polymer silane can be dissolved, first dissolved, and second, we can produce the membrane. But the strength of the membranes is low and the tensile is low. Valerolactone, you see the similar structure to the NMP and also used in the fabrication of the membranes. For fabrication of this valerolactone, this biomaterial is used, levulinic acid, separate from the oil, vegetable oils. The methyl isosorbate with this structure also is used in the fabrication of the membranes. Therefore, we can use the bio-based membranes for bio-based solvents for the fabrication of the membranes. The third group is green synthetic solvents. Green synthetic. That means that these solvents chemically synthesized, not in the bio-based, but the fabrication method and the properties of the solvent is green, and most of these solvents you see have a carbonate based. This is organic carbonates. This is organic groups. Most of these categories have this structure, and with change of this R1 and R2, we can change the solvent properties for dissolving our polymers. For example, this is the solvents used for dissolving these polymers, that's polyethyl sulfone, polysulfone, polyacrylonitrile, and others in this study, and shows that we can use most of these solvents in the fabrication of MF, UF, and NF membranes. With change of the solvents, this study shows that prepare the NF, UF, and MF membranes with polyethyl sulfone, PVDF, polysulfone, polyacrylonitrile, and obtained these membranes. The most famous green synthetic solvent is DMSO. DMSO traditionally is used in the membrane fabrication and have a similar behavior as DMAC, DMSO. The obtained solution is relatively high viscosity, and we can use this for fabrication of membranes. We have another green synthetic solvent as a Tomisolv. This is an NMP, you see, and this is the similar NMP, only have 3 extra aliphatic groups. The microorganisms mostly cannot be eat the cyclic materials or aromatic materials. Aromatics and cyclics are toxic for microorganisms. When we have this compound, this structure in the membrane, in the organic compounds, in the biodegradation, the bacteria cannot eat this one, but easily can eat the aliphatic. Most of the oils, fats, have this structure. And this fatty acids very easily eat with bacteria. In this case, this is a toxic, but this is not toxic, because these groups help the biodegradability of this solvent. Therefore, with change of a little change in the NMP structure and change it to the Tomisolv, we can increase the greener behavior of the solvents, and the microorganism can biodegrade these solvents. And this study shows that the Tomisolv can be replaced with NMP, and we can use these solvents for fabrication of membranes, but the price of Tomisolv 5 times bigger than the NMP. Why? Why expensive? Because low production. Because low production. Both the solvents is synthetic, but it is very usual from 100 years is used, but this is the new one. After 10 years, I think the price of this solvents should be similar, because we go to the greener solvents, and we're forced to use these solvents. Therefore, production of the green solvents will be increased and the price will be reduced. Another very green solvent is ionic liquids. Ionic liquids, mixture of 2 organic compounds, or 1 organic, 1 inorganic compounds. Then when we mix these 2 cation and anions together, we have a liquid. And this liquid can act as a traditional liquid, but very environmental friendly. Ionic liquids have not volatility, no vapor, and very good low vapor pressure, but very expensive now, very expensive. But the studies shows that we can dissolve some polymers in this ionic liquid, and we have many thousand ionic liquid with mixing different cations and different anions. Therefore, there are many ionic liquids, and we change the properties of the solvent with change of this group. We can have hydrophilic solvent or hydrophobic solvent, polar solvent, non-polar solvent. In this study, use the cellulose and this type of ionic liquids for dissolving of the polymers and fabricated hollow fiber membranes. Or in this study, dissolved PVDF HFP in this ionic liquid and fabricated the different morphology of the membranes. We have a software as LCA, life cycle assessment. That is very important that we calculate and see the different aspects of a process for production of a product, okay? With calculation of life cycle assessment, we see that our suggested compound or product, how can influence in different aspects of the environment. These compounds, how affect in the weather, how affect in the water, how affect in the soil, and others. So there are many, for example, eutrophication potential, how affect in the growth of the microorganism in eutrophication process. Human toxicity, This compound is toxic for human, toxic for vegetables. Photochemical ozone accretion potential, aquatic, very, very different, more than 20, 30. And in this assessment, we have a Simaporoma software. Name of software is Simaporoma. That assessment the life cycle. In this study, investigated the use of this ionic liquid and compared it with toluene and see that the ionic liquid is very good for environmental, but in this aspect, toluene is very bad. Therefore, if we replace this ionic liquid with toluene, very good for environmental aspect. And the final categories of the solvent that now is very important, this is the new solvents, is deep eutectic solvents. Deep eutectic solvent is similar to the ionic liquid solvents, but is very, very cheap. And fabricated, for example, from urea, glycerol. Oh. Urea is solid. Urea is solid. This compound is also solid. Oh. We have a donor and acceptor. Hydrogen bonding, like hydrogen bond acceptor, hydrogen bond donor. One give, okay? When we mix one HPA with one HPD, they contact together and mixing and reaching to a point that this point is named eutectic point, deep eutectic point, okay? We have also peak eutectic oil. Why say deep? Because in this deep. With mixing compounds, we go to the peak eutectic. That we see, this is the temperature, that we see that, for example, this chlorine mixed with the ure, okay? Both is solid. And when mixed to white solids and mixed, after 10 minutes, we have a liquid. We produced a liquid, a solvent from two solid with mixing. This is 100, this is 15. With mixing, we go to the 10 centigrade, and we have a liquid. And this is liquid is cheap because they use the materials, glycerol, ethylene glycol, urea is very cheap. And therefore, if we can dissolve the polymer in this deep eutectic solvents, we can prepare a green membranes. And these materials are not toxic. Urea are not toxic. Glycerin are not toxic. We use glycerin every day for our skins. Therefore, in deep eutectic solvent, we have a donor and an acceptor, and we can mix with different ratio. 1 mole urea, 1 mole chlorine. Or 2-1, 3-1 with different ratio, and we obtain different properties solvents, and we can use this in the membrane fabrication. The experiments showed in this study can fabricate PVDF membrane with this. Use 3 different DES, DES 1, DES 2, and show that we can dissolve the PVDF and obtain the different morphology and different pore size. It is very important. Now my 2 PhD students work in this area, and we published a review paper in 2021 about the use of this solvents as is a very important aspect, and in the future have a very good progress in this process. This is our calculation. We have another review. We suggest that which solvents can be used in the membrane fabrication. And in this table, we suggest for the first time that this can be used in the membrane fabrication with polysulfone, polyethyl sulfone. And we calculate Hansen solubility and shows, we say that the red RED is lower than 1, can dissolve the polymer. And we suggested that these solvents can be used in the fabrication of these membranes, and have a good citation, this paper, because based on this table, they select our suggested solvent and fabricate the membrane and say that we selected this solvent based on this table. There are some challenges with this green solvent. One challenge is the suitable viscosity. Usually, the bio-based solvents have very, very high viscosity. In use of NMP, dematch, traditional solvents, we prepare 20% polymer solution. That means we add 20 gram polymers to 80 gram solvents and prepare a good solution with good viscosity. But when we use the green solvent and we add 20 gram to 8 gram solvents, we have very high viscous solution, and we have to reduce the concentration of polymers. And when we reduce the concentration of polymers, we have a big pores. We want to prepare nanofiltration membrane, but because we reduce the polymer concentration, we have a microfiltration membrane. Therefore, one of the problems it is high viscosity. And when we use the low polymer concentration, our resulted membrane is very porous. And when it is very porous, the stability, durability is low. And the mechanical strength is reduced. In most cases, for dissolving of a polymer in the green solvent, we must use high temperature. In 25, in the air temperature, the polymer cannot dissolve. Therefore, we must reduce to 90, 100 centigrades and cast the high temperature. This is the second problem from industrial application and energy consumption. We have not used NIPS method. When we use NMP, dematch, and non-solvent is water, dematch with water is miscible. Miscible that when we add them, no two phase, one phase, okay? But in bio-based green solvents, because bio-based and such as oil, therefore no miscible with water. And when no miscible, do not want to go to the water. And we have not phase inversion. We prepare the film, go to the water. But bio-based solvent do not go to the water, and we have not good film. Okay, some problem. High price is very important. Our most ionic liquids and this have very low volatile, and the WIPs and IIPs for fabrication of the dense membranes in, for example, protein exchange membrane, we cannot use because they are not volatile and not vapor. And therefore, we cannot prepare a dense films. The researchers are in this area focuses and suggest new green solvent, deputectic solvent, ionic liquid for dissolve these talents. High price, this shows that the price of these solvents usually 3 times more expensive, but I think that will be reduced. Low strength, I say that these membranes usually have a low strength. Time is finished. The second aspect is the biopolymer used. If we can use the biopolymers in the membrane fabrication, after 3 years, 4 years, 5 years that the membrane is destroyed, we can degrade these biopolymers with landfill and other methods. Therefore, it is better we use the natural resource polymers such as cellulose, cellulose acetate, starch, lignin, and others can be used. Usually, today's focused on the use of polylactic acid. Polylactic acid is very good biopolymer for production of the membranes, and now most researchers focused the use of this biopolymer in the fabrication of different type of the membranes. Thank you for your attention.
Any question from the audience side?
Sir, LCA cycle, life cycle assessment.
Yes.
Out of all those parameters, which one will give more emphasis to determine?
For LCA assessment, we must give some information to software, and after giving this data, the software will calculate based on our dictionary, the software, Simaproma software, and predict and say that this, for example, solvent or this polymer or this method in all of them, from the economical view, how compare, you give some price of the materials, and mostly compare to, in the LCA, we compare 2, 3, 4 processes together, not one process. For example, you see, compare toluene with ionic liquid. In this case, say, based on our literature, our data. For obtaining this data, we usually use the other published literature, books, handbooks, Google's patents, and we, for example, we add boiling point of the solvents and other processes, molecular weight of polymers, prices, and if there are some papers that reported the durability, stability, chemical resistance, and everything. Add, and after that, the software run and calculate different aspects of the your process or your component. Okay. Very interesting software.
What's the software name, sir?
Yeah.
What is the software name?
Name?
Name.
Simaproma.
Simaproma.
Any other question?
Sir, like you mentioned that the deputectic solvents and ionic liquids, if they have high viscosity, you will get big pores, right?
Yes.
I have a doubt, we can actually tune the viscosity and polarity of these solvents synthetically.
Yes.
Then we can use, we can plan the desired polarity and viscosity, like if we want small pore size, so the viscosity should be low.
Yeah.
So we can tune them synthetically. So is that applied, is that mechanism applied in this membrane technology? That's the doubt I
Your question is the effect of viscosity on the membrane fabrication?
No, you already explained about the effect of viscosity on membrane, but I'm asking like, can't we tune them? Like if we tune them, the polarity and viscosity of deep eutectic solvents and ionic solvents to the desired ratio, and then we can utilize them.
Yes.
Is that possible?
Yes, it's possible. There are many cationic and anionic group in ionic liquids, and donor and acceptor groups in the deputectic solvent. With change of these groups, we can arrange the polarity, hydrogen bond, and also we can change the viscosity. And we can manage both viscosity and polarity. But one big problem is the buying of the materials. When you want to change many functional groups, you need buy 50 components and need the money. And therefore, these investigations needs very big grants and big projects. And usually in MSc or PhD thesis, we have not this money. And it is very good idea that we can manage functional group polarity and viscosity to give the better performance. In the most papers you see select 3-4 days based on our calculation and published paper and investigate them. Therefore, most want to prepare a good membrane, not control the viscosity, but if possible, but need a very big project.
I just would like to add one more thing here, because when I was doing my PhD, one time I was working on a membrane with polyaniline, and where I already had a zinc chloride as an additive in the membrane. So what I was seeing is that my membrane was very spongy type, and the viscosity of the solution was very low. The membrane was having very spongy nature. So from a low filtration with just variation of polyaniline from 1 to 4%, the viscosity varied in such a way that it actually went from a non-Newtonian behavior of that casting solution to almost a Newtonian behavior, almost a straight line we obtained in a rheometer. And there was a huge variation in pore size with the variation of polyaniline, because polyaniline was changing the viscosity to a very large extent.
Yes.
So not only the thermodynamic aspect, but I think the kinetic aspect also comes in picture, which actually influences the pore size or the pore distribution inside the membrane.
Yes.
So there are a lot of studies going on, and there are huge scope of more research.
Yes. Also, I say that with addition of some particles, some polymers, we can manage the viscosity. For example, we want to prepare microfiltration with big pore size. We want to have a low amount of polymers. For example, 6%. But in 6% PVDF in DMAC, the solution is very, very low viscose, and we cannot cast. In this case, add 10% polyethylene glycol. Polyethylene glycol is soluble in water. With addition of polyethylene glycol, the viscosity increase, we can cast, but during the phase inversion, the polyethylene glycol go to the water and also increase the porosity, and also we manage the viscosity. Some salts reduce the viscosity.
Thank you very much for your insightful talk. And so now we will proceed for a small tea break.
Okay.
After that, in 15 minutes, we'll gather here in this room.
Thank you.
Would you like me to go in the next because
Okay.
What secret did the richest man in the world share with Napoleon Hill?
Yes. And actually, XRD is the based on principle of the Bragg's law. It is a n lambda is equal to 2d sin theta. Based on principle, it is working. So inside the XRT, there is a 4 components. One is the X-ray tube, one is the stage, another one detector, another one goniometer. So X-ray is coming from the X-ray tube, and it will interact with the sample, and from the sample it diffracted, and directly it is collected by the detector, and it gives the peaks. So based on peaks and the position of the 2 theta, we get the some despacing values. Based on despacing values, we can identify the what is the composition of the mineral. Like that, we can identify the phases of the sample. That's it.
Now okay na sir? Now okay. Yes. Vocation, I think she needs a AC remote. মেসেজ করতে হবে না, আমি সকালবেলাতে সবাইকেই সকালবেলা সবাই start. So good morning everyone. Am I audible? Okay, clearly? Okay. So in this session today, I am going to talk about some future trends with the membranes. Okay. So in these days, we have been talking about membrane fabrication, membrane application, their characterization, how to test the performance. Many things we have been talking. We have discussed about the hydrogen energy also, how the membranes are doing. Now, one thing that I would like to discuss now is that membrane is here from a very long time. So membrane has gone through a lot of development, lot of innovations through them. But still, day by day, it is finding more and more application, more and more scope for its application and even betterment of these membranes. Okay. So that is why it is very important for us to be future ready, and let us see that where our future with membrane lies. Okay. So in this session, I am going to talk about the technologies which are going to be very, very prominent in coming years in life, in our life. So one of the very important aspect of membrane is the nanostructured membrane. So this term of nanostructure, it got a boom very recent years ago, because many people can found that nanoparticles actually giving you much more surface area at per unit volume or per unit mass. So that is why they have very, very advantageous application, provided you can stabilize them. Okay. So among the materials which are very popular or going to be very useful in recent years, they are graphene based materials, MOF or metal organic framework material, bio-inspired material like some mimicking the biological properties of different animals and plants. Also there are hybrid nanocomposite membrane like combination of organic and inorganic material. They are basically some of the structures or some of the categories where we found significant development. Like with this development we can achieve very high proton conductivity, we can increase the durability of the membrane. We have been listening about LCA in our previous lecture. So LCA is basically has been done for many of these applications, and it has been proven that they have a very good lifespan and end of life usage. So efficiency is that they can offer you better efficiency also. So in future they are going to have more application in the nature and all. Now one thing we can be discussing here is that nanomaterials can be 0D, 1D, 2D or 3D. Okay. So like say graphene based nanomaterials, 0D materials, famous example is quantum dots. Okay. So and also in the 2D material graphene or graphene oxide, that is one of the carbon nanoparticle. So we also have 1D material which is like carbon nanotube. Okay. So like this we can have, and 3D material they call it carbon nanoanion, which is slowly developing in various sectors of application. So like this you can have different dimensions of your nanomaterial, and you can tune the properties for transport of different ions. You can have surface interaction with different contaminants or components. You can tune the structural properties of the membranes. So like this, these are some specific applications that we are going to see in recent years. Now PEM or polymer electrolyte membrane, we have talked quite a lot in my sessions till now. So PFSA or fluorosulfonic acid, non-fluorinated hydrocarbon membranes, they are not only very highly efficient, they are more stable, and they are people all over the world, they are trying to find even more cost effective solution for these membranes. Okay. So for this we can have these membranes with a durability concern. Durability is very good, proton conductivity is very good for PEM. So this is one of the sector where PEM is even going to develop much more in recent years, which is already developed, and even much more further development in future directions we can expect. So we have talked a little bit about the water channel. So what does a water channel tells you is that basically when we are having a PEM membrane, the pores are very narrow, or the membranes are very dense. So in that case we do not allow free flow of water through it, water molecules through it. So what we have is that these water channels where we have arrangements like this. So these walls of these channels are basically made up of hydrophobic backbone, and the inside of these channels are made up of hydrophilic side chains. So that is why this is basically hydrophilic regions bounded by your hydrophobic backbone. So that is why their channel dimensions are given like this, that this is around 40 Armstrong and 10 Armstrong of channel, continuous channel, and around average 50 Armstrong of distance between two clusters of such channel. So like this we have a tentative idea which we can get more detailed view of this microscopic analysis to get the channel dimension of our water channel. Basically our water molecules, they flow through them like this. So by effect of intercharging of these negative ions and the positive ions, the water molecules, they can drive themselves very effectively. So by either by hopping mechanism or by vehicular mechanism, this is the Nafion cluster that we can look into for more engineering. So one thing I would like to mention here, there is a famous approach for enhancing of this water channel called microphase segregation. So what is microphase segregation? Microphase segregation is practically the making these arrangement of my water channels better. So what are some options that we can look for microphase segregation is that we can apply for, we can have specific materials of construction, we can do some post treatment, like after casting the membrane we can expose it to the polar and non-polar solvent. So if we expose it to the polar solvent in order to reduce the free energy, they orient the functional groups, they orient themselves in such a way that our water channels, they become very, very stable. Okay. So these are some of the factors of microphase segregation that I am working on, and many people all over the world are working in that direction for betterment of membranes. So one membrane material that is very effectively applied in various technologies is the ceramic material. For that ceramic material, what we have? We have mixed ionic and electronic conducting material. So that means they can conduct, some part of it can conduct protons, some part of it can conduct negatively charged ions. So like this we can have ceramic membranes oriented like that. We can have perovskite based material. So do you know where this perovskite find most of its application? Most of it solar. Why it is so very, very applicable in solar category? Because it has a lot of absorption capacity of photon, light photon. Okay. So that is why perovskite is a very popular technology wherever we have a very good application of solar power. Okay. We can have dual phase membrane, which is mostly useful for carbon sequestration or CO2 separation. We can have nanostructure ceramic coating over a polymeric substance. So when we are talking about composite membranes, we talked that we can have dual layer, we can have coating of ceramic layer over a polymeric substance. So these kind of materials are very, very useful for ceramic membrane application. Okay. So we have operating temperature for this particular useful thing for ceramic is that they are very, very highly temperature stable, they thermally stable. Okay. So if you have very high temperature application, so then you can have you can go up to 600 to 1000 degrees centigrade with this type of membrane. They have good hydrogen permeability and they can gain efficiency also. So with these aspects we can have a very good application of ceramic membranes. In this slide what I am showing you is a specific case study with ceramic membranes. So this is a particular work which is reported in this paper. So what they have done is that they have made ceramic membranes of with channels of different structures. Okay. And inside these channels they have input some polymeric material. In that way what they have done is that this ceramic material is actually was absorbing some particular contaminant and this polymeric material was doing the size seclusion preparation. Okay. So in this way what they could do is that from a raw water data, from a raw water like surface water they used like pond water or river water, and from that they removed these smaller contaminants by adsorption with this ceramic material and by size-less separation with the polymeric material embedded into it. So at the same time they are removing the bigger size and smaller size, like more or less combining the primary and the tertiary treatment of the water. Okay. So this is one of the example that I have given. You can even immobilize some biomass also in the pores or the openings of a sea or ceramic. That is one more area that we need to develop or work more on that area. Okay. Going to the fourth technology, one thing that many people are very, very much concerned about today is the CO2 absorption, CO2 sequestration. So now in order before talking about its application of this membrane for this particular category, we need to understand that what type of carbon sequestration we have or we can see in our life. So, something is called direct air capture. So, our air contains around maximum around 4% of CO2, okay. Generally it is less than that only. So, this around 400 ppm we have. Now, if we are capturing the CO2 directly from the air, so that is the direct air capture. So, for us our very good friend trees are all around us, but many people are using the artificial photosynthesis where they have shown a better efficiency for direct air capture of CO2. Okay. But apart from that, two things are something which mostly people are working on. One thing is that post combustion and pre combustion. Combustion of what? Combustion of basically the fossil fuel, okay, which we are using for energy generation. Now, if we want to capture the CO2 before the combustion, then CO2 whatever we have around before combustion, if we have certain CO2 percentage, and if we convert it after the conversion, we have certain CO2 percentage. So, we can have this CO2 capture either before or after the combustion process. Okay. One more thing that we can do is that if we are only providing oxygen for the combustion, if we are providing air for the combustion, then obviously the CO2 concentration in the after combustion, the concentration remains lower than this. Okay. So, if we are providing only oxygen, lots of CO2 coming out. So, in all these cases our CO2 capturing efficiency varies quite a lot. We can also have chemical looping like conversion of CO2 into another form like methanol or something. And finally, what we do is that all of this goes for CO2 sequestration and utilization. Now, this direct air capture has a very low carbon CO2 concentration in the feed, and as we go down in this direction, we see that there are the CO2 concentration goes high in the air that we want to capture the CO2. Now, in all these sector, one very popular choice or mostly commercialized technology is amine absorption. So, MEA is a very popular solvent among the industrialists. What they do is that they do the absorption of CO2 directly. Okay. So, this absorption of CO2 amine, if we see, this is the normalized energy requirement for amine, the red line. Okay. Now, in place of amine, if we have some membrane with CO2 absorption capacity, we can reduce the energy requirement to a great extent, because the membranes are very highly scalable, much less energy requirement. So, with these things, these membranes can be of lower cost. Now, here I would like to add one more thing is that whenever we are going for aiming for any technology to be commercialized or widespread application, we have to do a techno-economic analysis for a particular technology that we have developed. Okay. So, in that techno-economic analysis, one term is always very important, that is called the levelized cost of energy. Okay. So, that is the LCOE. So, in this LCOE, what we generally consider is that we consider capex cost, that is the capital cost, that what cost we need for making up or setting up of this technology. Another is the OPEX cost, what cost we require for the operation. Okay. So, there are some more things also like depreciation cost. So, with time the value goes down. So, with that depreciation cost, what is there. So, also there are some other technology factors like manual input that we give. Okay. So, that cost. So, all these category or including all this category, we kind of fix a charge for per kg of operation or per kg of CO2 adsorbed for this case. If we determine the LCOE, there are some formulas specific to different technologies. So, if we calculate the LCOE for amine based technology and membrane based technology, always we will see that the membrane is giving you much lower LCOE. One of the main reason is that amine or MEA itself is a very costly solvent, and in order to regenerate the solvent, the process that we have, that is also very, very costly. But compared to that, membranes are much more efficient. So why this membrane gives you lesser LCOE or more efficiency is that they have very selective, permeability is very, very selective. You can tune them. You can have high permeance, you can have good energy efficiency, scalability, and you can easily change the modules of the membrane. And also the membranes that we have can be either polymeric or inorganic. Inorganic material can be MOF or zeolite. MOF is a emerging technology for capturing of CO2, and also you can have silica and high durability and selectivity for this kind of material. Okay, and also in industries also many people are slowly moving to the natural gas processing, industrial flue gas treatment, and for hydrogen production, co-production of hydrogen for CO2 capture. So all those things is actually giving you a good advantage with membranes. Okay. Okay. So next thing that we would like to discuss is biomimetic membrane or bio-inspired membrane. Okay. So in biomimetic membrane or bio-inspired membrane, the concept is that we have lot of physiological activity going on inside our body or any animal's body or any plant's body. So we are trying to replicate those functions in terms of membranes. So how can we replicate? We can replicate it through the structure, like we can have biological channel, nanoporous membranes are one of the example of that. So the cell membranes that we have inside our body, they have small channels through which the water and the nutrition that passes through our body. So this is one of the channels. We can have patterning onto the membrane surface, we can have etching onto the membrane surface, and can have a very uniform structure of nanopores. Okay, so this is one of the biomimetic application of membranes. We can have self-cleaning. So you have seen lotus leaf. Lotus leaf, the wet, it cannot get wet. Whenever a raindrop falls, it just goes down. Why? Hydrophobic. So it is a very hydrophobic in nature. So people try to incorporate that into their into the membrane structure. So do you know it has got very good application in coating of car front glass. Okay. So if you have a coating of this self-cleaning adhesive or self-cleaning properties onto a car surface, the water will not stick onto it. So you will get a more clear view when you are driving your car. Okay. So this is one of the application when you have a self-cleaning properties. Some people are trying to incorporate dissociation of water into this category, but obviously it has not been very useful or very efficient in a large size, but in small scale people have been people have used TiO2 or similar component to break this water molecule. We have other things like bioadhesion. Okay. So bioadhesion is like very much like when we apply a band-aid onto our surface. Okay. So like this, there will be some kind of adhesive or some coating material which will hold the layer by layer assembly of our membrane. So whenever we were talking about layer by layer assembly of our membrane, one thing we mentioned that whenever I have a layer by layer assembly, sometimes the top layer they get eroded with a prolonged use. Okay. In order to improve over this challenge, one thing that they do is that they use many types of additive or for adhesion. So it is very much like a band-aid, and you can have biomineralization for that, mimicking that is a hybrid membrane where small particles get decorated inside the membrane like mixed matrix membrane. You can have nanoporous membrane like self-assembly. So these are anti-fouling property of the membrane, like they do not let the contaminated molecule to sit onto the pores or the pore mouth. So for that, this glycosylmembrane or zetrionic membrane, they are very much useful for this anti-fouling property. Okay. So these are many bio-inspiring application for this membrane. And as I was telling that you can have different designs and different fabrications method for depending on which type of method you are going to replicate. You can have its application in water purification, energy storage, healthcare, gas and chemical separation, etc. But the main challenge for this is the durability. Okay, durability and scalability. So whatever we replicate, it has to withstand the test of time. So and it has to be reproducible in a larger scale. So that is why these two things that we need to work upon. We need to have a lot of research in this direction. Okay. So the next technology that I would like to talk about is the electrospun membranes. Okay. So what is electrospinning? Electrospinning is basically we are applying a potential field. Okay. So how we are applying? We are having a solution prepared, we have a solution loaded syringe. Then while doing the formation, then we apply a voltage across it. Okay. So when we are pushing the syringe, when the fluid or the polymer solution is coming out of them, it is like if we apply some voltage, they will orient themselves in a particular direction. So we can have a very uniform structure or the rod like structure, they will be very uniform for this kind of membrane. They are very useful for purifications of many small contaminants like microplastic. Do you know where we get microplastic formed very effectively in our water, contaminated water? Microplastic. So, bottles. Yes. So now bottles are like, so in order to take the bottle from its own form to the microplastic form, you need to have a lot of mechanical energy that between. So I was asking about ready-made injection of microplastic, not before microplastic, what was it? Okay. So like say lot of us used face wash with a scrubber particles, right? And we have, toothpaste will also have some small particles. Okay. So these are some common cause or common source of microplastic which goes every day to our water system. Okay. And for removal of them is particularly difficult because they are so small in size. Okay. And so that's why electrospun membrane can be a good option for this. So the advantage for them is that they provide a very high surface area. You can tune the porosity, it will give you a strong mechanical property, and that is why they are very useful for energy application. So the applications that you can use it for is that fuel cell, lithium ion batteries, supercapacitor, solar cells, etc. But one thing is that the scalability, and also because we need a stable electric field in this case, so that's why the fabrication cost also needs to be taken in mind. Okay. Okay. Graphene. So graphene is so popular, so useful that its origin, the person who discovered graphene was awarded with a Nobel Prize. So now the key advantages for these graphene based membranes are that graphene is much developed now. So we have a very ultra thin, we can make very ultra thin membrane providing very low resistance, so very good permeability. We can have very good mechanical strength also because between layers the bonds are very strong, you can make it very strong. You can make it very highly energy efficient by, you can impart many functional groups onto your graphene. Okay. So if the permeation of selectively hydrogen or the fuel enhancement, those are even in desalination and filtration, they have been proven to be very useful. But one challenge or one thing that we need to work on is that the scalability issue and the cost optimization, because whenever we talk about graphene being used for a industrial application, the main question or the first question that people ask is that how much is the cost? because graphene production is still now very, very expensive. So we have to make a more economical option to produce the graphene. Okay. So like say in this particular paper, they talked about graphene, application of graphene, functionalized graphene into a fuel cell based system. Okay. So what they did is that they made, in this particular work, they made different types of graphene and they functionalized the group with different materials, and then they used for in a anode and cathode, they used different chemicals. Okay. So then they, in this particular paper, they showed that just by changing the functionalization of the geomembrane, this geomembrane was used as an electrolyte for this type of fuel cell. Okay. You can have different materials into your anode and cathode, and you can produce hydrogen, and you can get energy with these different materials if you just change the functionalization method of your graphene membrane. So this is one very impactful research I feel in this particular area. So one more thing that we have been talking about a lot is the surface hydrophilicity. So what is the method that gives us an idea about surface hydrophilicity? That is, the method that we practically use to measure the hydrophilicity of a membrane surface, that is contact angle measurement. So we drop a drop of water onto a membrane surface and measure the contact angle, as professor has explained it in much detail in earlier session. So what we can see from this particular work is that this particular work, they reported many membranes with different composition. This is a work on a composite membrane. Okay. So with different compositions of the additive, they had a nanoparticle additive, and they had a contact angle being varied, okay, up to a certain angle. So now that if we see that the contact angle being varied and the water flux was also being varied due to mainly because of the hydrophilicity and hydrophobicity of the membrane. So now the one thing that comes into picture, that hydrophilicity will obviously be helpful if we have to preferentially try to send the water through it. Okay. So in order to increase the hydrophilicity, we can have options like bio-inspired hydrophilic surface, like some having some functionalization onto your membrane surface, which is like very much like the top surface of our skin, or you can have graphene oxide membranes or anti-fouling hydrophilic coating or hybrid membranes, etc. Hydrophobicity, you can have hydrophobic coating if you want to use hydrophobic membrane. Hydrophobic membrane is used in where? In different petrochemical industries. Hydrophobic membranes are used for, particularly it is sometimes used for enhance the efficiency of oily water membrane. So like that. So super hydrophobic coating we can have electrospun membrane, we can use plasma treatment for increasing of hydrophobicity of your system. So like these membranes can be tuned to change their hydrophilicity and hydrophobicity, and there are a lot of routes which we can be wherever we can make it more existing or more durable, we can have the membranes like that. Okay. So the hydrophilic membrane, they have got its application in ultrafiltration and RO treatment. Hydrophobic membrane is very useful in MD or membrane distillation. In the fuel cells, we tend to use more hydrophilic membrane in PEM, because in the PEM we need water to carry the H+. So that's why hydrophilic is more preferable. For gas filtration, if we want to gas filtration, for that industrial filtration, for that we need very high flux. So that's why application of hydrophilic material is important. If we want to separate the CO2 from the VOC, volatile organic carbonate, okay. So in that case, hydrophobic material will be very, very useful. Okay. So any question till now? Nothing. Any question? Yes.
You just told like in order to separate carbon dioxide from volatile organic.
Yes, yes.
Can you understand like how will you separate that?
How will you separate?
Hydrophobic membrane.
Yes. So basically VOCs are sometimes thought, what are VOCs? VOCs are basically evaporated organic component, right? So in that case, they have a very much oily nature, most of them, okay. So if you have a hydrophobic membrane, so it is very much easy to the preferential transport of this oily material through them. So that is why you can separate out the CO2 and VOC easily, comparatively, for this kind of application. Okay. So let us proceed to the next topic, that is the photocatalytic water treatment. So in a photocatalytic water treatment, what we do generally is that okay, one traditional application of membrane is the size based seclusion. Okay, so like big size contaminants will be retained by your membrane when you are applying it. Now many people they mentioned it as a way to like enhance this property, or as a way to go forward for widespread application, that what we will do with the reject water, the retented stream, because it is highly contaminated with what contaminant, right? So even the RO reject, the retented side, so we need to regenerate, or we need to have a separate process for in order to make it safe for discharge to the environment. Okay. So one of the route for this is that to overcome this challenge is the degradation of these contaminants, okay, degradation to a safer alternative. So now degradation, how you will do? You will break down this chemical by some dissociation mechanism, and now imagine you are using solar light to make this degradation possible, and that becomes a photocatalytic water treatment, which will lead to from organic to an inorganic end product. Okay. So in this case, if we have photocatalytic property of photocatalyst embedded onto your membrane, let us say that I have TiO2 embedded onto my membrane, okay, I have TiO2 decorated onto a membrane surface, and I expose that membrane inside water to a light source, okay. So then they will generate many free radicals and will attack the organic component that is there inside your membrane. If I show you this slide, you can see that this is where the photocatalyst particle is suspended in your system. Now before removing this, before using this water, we need to separate out this photocatalyst particle also, otherwise this will not be safe for consumption or safe for further use. Now if imagine that onto this membrane you immobilize this photocatalyst. In that case, you are using this catalysis, this organic dissociation and membrane filtration at a single step. So that is how photocatalytic water treatment is very much useful for this category. So practically we are working on this area also. So if any of you are interested, we can show you one operation of such a photocatalytic water treatment activity. Okay. So some of the examples that we have for a photocatalytic membrane, so some of the options that we have for this photocatalyst is that the TiO2 based membrane or zinc oxide or carbon based membrane or hybrid material, etc. Now one thing we need to keep in mind that be it TiO2 or any other contaminants, when it is generated by, or when it is excited by UV light, the UV light carries more energy. So when it is excited, when UV light falls on them, they will be giving you, they will be generating more and more free radicals, and you will see more degradation. But UV light is also very corrosive and also very expensive. Okay, so that's why the focus is going to shift from UV light towards the visible light application. And what do we need to do for visible light application? We need to reduce the band gap between the valence band and the conduction band. Okay, and in order to reduce the band gap, one of few possible technologies are the sintering of the membrane or doping it with a secondary substance. So that is why sintering of TiO2 or zinc oxide, carbon, specially engineered carbon nanotubes, they are just being very focused upon, because they can shift our UV light activation towards the visible light activation. That will be a more sustainable solution for all of us. Now fouling. So we have been talking a lot about fouling, regeneration, those kind of operation, because fouling is a traditional phenomena of a membrane filtration process. Now let us see how a fouling occurs in a pore level. So basically when we have some contaminant being filtered through a pore to a membrane, the contaminant materials, they sit on the sides of the pore. Okay, so that we call a partial pore blocking. Okay, so the pore is partially blocked. So now your road to move for the water, they become restricted. So obviously you mention or you get lower flux. Okay. Sometimes with a prolonged use, what you can expect is that the pore is fully blocked. So there is no more way left for your water to go. So this is full pore blocking. Okay. Apart from that, one more thing that is very common in especially gel layer filtration is that you will see that small colloidal particles are accumulating onto your surface. It is like making a cake of gel layer over your surface. Okay. So this is cake layer formation. Okay. So these are three types of stages of fouling that you can see in a fouling mechanism. Okay. Now in order to mitigate this fouligation, or it is not possible to completely mitigate this fouligation, maybe you can reduce it. One way to do that is that you can enhance the Reynolds number onto your membrane surface, okay, so that you are not letting the contaminants to sit on the pore or the pore mouth. So that's why you can have, the way to do that is that you can have some hydrophilic coating, you can have stimuli responsive membranes. Okay. So like say if you apply the voltage potential, the contaminant will just lift off from your surface. Okay. This is one of the technologies that electric enhanced ultrafiltration, ultra and microfiltration, we do work on these kind of membranes. Okay. There are some nano composite membrane, we can have some surface modification, we can have some operational strategies like self-cleaning membrane or backwashing, etc. We can have chemical and biological control, etc. Okay. Now one thing that is a very hit word nowadays, that is AI and ML. Okay. So AI and ML, how can we employ the artificial intelligence or machine learning in membrane related work? So membrane needs a lots of optimization. One of the first thing to optimize is the composition of your membrane. Okay. So now let us say that today only we were talking about the viscosity, how does it affect the pore size of the membrane, and professor was talking about there are many options for us to regulate the viscosity, like salt, like different polymers. Now let us say that I gather some data for many effect of many salt and many polymers. Okay. If I have sufficiently large number of data pool where I can optimize these structure or these what are the effect of different salt and polymers, then I can identify which salt or which polymer is going to be the optimized composition of our system. Not only that, I can also have different operating conditions. If I want to know the different effect of temperature, effect of pressure, or effect of surface Reynolds number onto my membrane. So particularly which composition to use in order to enhance the anti-fouling property of my membrane, in order to enhance the scale up process of my membrane. So with these things, rather than having a lot of experimental data, if we use AI and ML for this kind of category, then it can be very, very useful. Okay. We can have optimized membrane composition, we can have optimized membrane operation, so all those things. Okay. So what are the options that we can do is that we can do it for high throughput, computational simulation, etc. We can have predictive modeling, like say all the data given, then if I have a new membrane composition, then what will be the characteristics of my membrane. We can have some smart membrane systems, like if they are going to tune their own property with the change in the environment, like that. Okay. Okay. Now let us talk a little about the ion exchange membranes. Now, ion exchange membrane is here for quite a long time, because in what do we need, what do we talk about ion exchange membranes? Let us say I have a negatively charged membrane into my surface. Now, one thing we have been talking about is that the membrane zeta potential, it is very much dependent on the pH of the system. So, we have a ZPC value of a pH where the surface charge is 0, and below that it is negative, and above that it is positive, the opposite way. So, now if we have the negative charged membranes, now it will facilitate the transport of positive ions, but it will repel the negative ions. So, in that way we can enhance the separation of the chlorine and the sodium with this cation exchange membrane. We can have anion exchange membrane where the membrane is positively charged, which is transporting the negative charged ions and just rejecting the sodium. So, in that way what we have in an ion exchange membrane is that by tuning the surface zeta potential or surface charge of the membrane, I can have a ion based separation of my system. Okay. So, now this is a very popular choice for electrodialysis, very popular choice for desalination application, etc. So, now mainly we have a cation exchange and ion exchange membrane and some bipolar membrane, where by changing the surrounding pH we can very easily change the surface charge. We can have mixed ion exchange membrane also. So, these are very much useful for electrodialysis and reverse electrodialysis that I was talking just now, and for desalination application, even energy generation, they have got its advantage. Application. They give you very high selectivity and efficiency, and it requires a very low maintenance because fouling is very low or pore blocking is very low for this kind of membrane. And chemical composition also, you do not need to add a lot of expensive chemicals for this kind of treatment. So, that is also very low, less chemical composition. Okay. Now, here I would like to talk a little more about the DMFC or the direct methanol fuel cell. So, we have talked a lot about PEM, AEM, etc. Now, in direct methanol fuel cell, what we have here is that we have methanol as a fuel of the system. Okay. So, in this anode chamber, methanol is given, and the cathode chamber we have air. Okay. Now, this methanol is transported and H plus is transported from the anode side to the cathode side. These membranes have a very similar nature to that of Nafion or the PEM membranes. So, many often you will see the direct application of Nafion and all, but one particular criteria for this kind of membrane or this kind of DMFC application is that they must have very low crossover of methanol. So, the methanol permeability through these membranes should be very, very low. Okay. And that is one of the main bottleneck or main challenge many people are facing for development of this kind of membrane. So, in that in order to do that, what are the options that we have? We can have Nafion based membranes, as I was telling that they are most often directly used. You can have sulfonated polymeric membranes also. You can have composite or ionic or anion exchange membrane, etc. So, one challenge that we have is the methanol crossover, crossing of methanol from one side to another side. Durability and stability is very important for these membranes. So, we need to enhance upon that. Okay. So, this is the DMFC. Okay. So, now here we have talked about biomimetic application, but biodegradable is something which is essential for sustainability of our operation. Okay. So, in a biodegradable operation, what we can have these membranes used for, even the membranes can be used for water filtration or for medical application, where part of the medical replacement category device is made up of made up of these membranes. So, you can have options like cellulose, chitosan, etc., which are proven to be very, very bioavailable, that means that it is highly biodegradable, so that whenever the operation or the lifetime of the membrane is over, you can use it for safe operations like land filling or making of structural materials, etc. Okay. So, one of the future direction is that membranes are very widely used for membrane hydrogen generation, electrolyzer, and also they are with carrying of the membrane. For that we have talked about the hydrogen storage and hydrogen application, generation of electricity through fuel cell, etc. For that we have, so now one thing I did not mention very elaborately onto this is that membranes, for whenever they are used in high scale operation like MCFC, SOFC, they can give you the power to apply the current to the flow of power to the grid. So, for that what we can need is that the fuel cell stack that we have, we will generate the DC power from it. For that, after that we need an inverter and transformer, because before it can be given to the electric grid. Okay. So, this is one of the application where this transport of from the fuel cell to inverter, many people are working on this, that which of composition will be giving you a better of this conversion. Also, these membranes are in the fuel cell, they are used in many industries like fuel cell, aerospace, chemical industries, etc. They can take their power from renewable sources like hydropower, solar energy, wind power, etc. If they take renewable energy sources for hydrogen generation, they are really green technologies. Okay. We can have some, we can have for different industrial application, we need hydrogen. So, in that case, we need membranes in these operations like SMR or steam methane reforming, water gas shift reaction, ammonia cracking, biomass and waste gasification, etc. So, in SMR we have the role of membrane is to continuously hydrogen to be shift to the equilibrium for higher methane conversion using the Lash-Atelier principle. For WGS, it is basically the separation of hydrogen where the membrane comes in picture. So, for ammonia cracking, we generally use the hydrogen generation for fuel cell application. For biomass and waste gasification, the membrane provides more surface area for the conversion or for higher level of mass transport. We can have metallic, inorganic, polymeric and composite membranes for that. I would like to give you a small example of this kind of operation, like here in this particular paper they developed a membrane where you have a composite structure. They had in the feed side they had a hydrogen and toluene mixture gas, and what they saw that they made a selective permeability of their membrane and packed it in a glass casing, and from there it was allowing only the hydrogen molecule, not the toluene molecule to go through it. So, in the tube side basically in the shell side they have a mixture of gas, but in the tube side or the permeate side they are only getting the pure hydrogen gases. Okay. Reverse electrodialysis is basically here we are having reverse electrodialysis is one of the very efficient operation. So, and very recent developments. So, here basically we are giving a energy load. Okay. So, by using the cation and anion exchange membranes sequentially, we can have the concentrate solution and diluted solution in a batteries like lithium ion batteries and solid state batteries, they also get very good application of membranes also. So, where the in the lithium ion batteries we basically have liquid electrolyte, but there is a separator which separates the anode and cathode chamber, and there we have the membrane being effective. But in solid state battery what is different is that we only have a solid electrolyte and that is basically the membrane that we are using for the solid electrolyte. So these membranes, they need for charging and discharging, they will be very useful, and they need very small space for this. So from a big size of lithium ion battery, we are able to convert it to a solid state battery, and for that a particular compositions and particular permeability, not permeability, but particular ion conductivity, those are very important for use in the solid state battery. So the options that we have for solid state batteries are that you can have polyphene based separators, or you can have ceramic coated separators, electrospun or more regular membranes, or gel polymeric electrolyte, etc. So these were some of the recent trends in the membrane filtration technology and for energy application and environmental application with the membranes. And we had an overview of all the purification technologies and the energy applications. So not only these technologies, there are much more opportunities for the membranes to develop and to carry forward their role in the industry and their recent futures. So we need to focus on these areas and some more other areas also, so that we can have a more sustainable option, more energy efficient option for this kind of technology. Okay. Thank you so much, and if you have any question, please let me know. Sorry?
Do we get hydrogen from DMFC?
DMFC, yes.
Yeah.
We make hydrogen from DMFC. So basically fuel cell is for generation of electricity and electrolyzer is for generation of hydrogen. So electrolyzer is basically which is separating between hydrogen and oxygen. DMFC has a very similar operation like PEM. So PEM electrolyzer is giving you hydrogen, and fuel cell is using this hydrogen to generate electrolyte, to generate electric.
So in DMFC we use the hydrogen we don't get, or we can get like.
We can get if we use these membranes in an electrolyzer mode.
Okay.
We can get.
Okay.
Yes. Any other question? Yes.
Ma'am, for anti-fouling membranes, you mentioned in one of the slides that we are making the surfaces hydrophilic. Generally, if you increase the hydrophilicity, the attracting of more amount of fouling agents on the surface increases, or it is vice versa.
So basically, let us suppose that you have a mixture of oil and water. Okay.
Yes, ma'am.
So now water is very, very hydrophobic. Oil is hydrophobic. Okay. Now, if your membrane is more hydrophilic, that is, it passes the water more through it, more its water channel. So then, in between this water and oil, which is more likely to go through your membrane pores?
Okay.
Water, right? So that's why oil will be retained onto the retented side, onto the permeate side, you will get the water. So like this, many of such contaminants are more hydrophobic. So they will be retained, they will not be prone to go through your membrane pores.
One more question related to what is meant by air scouring, ma'am. You said you shown one of the technique to enhance the anti-fouling on the surfaces. There is a technique called air scouring.
Air scouring?
Air scouring, SCOURING.
Which slide?
In slides, like in the slide of fouling prevention mechanisms you shown. Next one, ma'am. Here.
Okay. Air scouring is basically for loosely attached particles,
Okay,
which
ma'am.
particles are loosely attached onto a membrane. So it is just passing your air at a very high velocity over your membrane surface, so that they can serve two purposes. Either if it is very loose, they can detach themselves the contaminants, or otherwise they can loosen the bond between them, so that when we are doing the chemical and chemical cleaning onto the membrane, it will be more useful. So that's what is.
And one more question with respect to the silver nanoparticles that actually act as a anti-foulant.
Yes, yes.
how actually the functionality will be there, ma'am? Like for example, if I used for RO membranes or microfiltration, any membranes, when we are adding these nanoparticles, how this act as a anti-fouling agent? That means mechanism. What is the mechanism behind it?
Yes, there are two things that the silver nanoparticles contribute to. One is that silver is a very good antimicrobial agent. Okay, so whenever you are talking about making its use in a water purifier or such system, their main purpose is to impart the antimicrobial property. Second thing is that the silver nanoparticles have got very low contact angle. So, effective contact angle or effective hydrophilicity, when you are making the silver nanoparticle induced into your membrane, the effective hydrophilicity goes up for your system. So, that is the two mechanisms of silver nanoparticle. But one thing you need to keep in mind, that silver is itself is costly. So, when we are trying to use the silver nanoparticle for industrial application, large scale application, we need to keep the cost in mind.
Okay. Thank you, ma'am.
Yes. Any other question? Last bench.
Regarding biomimetic membrane, compared to conventional one, what is the limitation and some challenges we are facing now?
Limitation of what?
Biomimetic membrane.
Biomimetic membrane.
Yeah,
What
yeah.
are the limitations?
Yeah, and the challenges.
Yes. So, limitation basically for biomimetic membrane, most of the limitation or biggest challenge is scalability. So, let us say that I need to use a aquaporin. Aquaporin is a substance which is found in cell membrane, live cell membrane. Okay. So, it is basically a vehicle for transport of your nutrition and water inside of your membrane. Okay. So, many people are trying to use properties like aquaporin inside your membrane. Now, aquaporin itself is very, very costly. So, if you want to use it for a very high surface area, then the cost will be very huge. Okay. And also let us say that I want to have a self assembly, that I was giving you a patterning to be one of the possible biomimetic route. Okay, patterning in a very small membrane area, it is very easy. But if whenever you are going to for scalability, then the patterning is difficult. Like difficult in the sense that they do not stay intact for a very long time, and also patterning in a high surface area for a longer for an industrial application also, cost goes very high. So, these are the main two challenge for biomimetic application, but if we can do it, it will be very useful for us. Any other question? Okay. So, no other question. So, thank you all for your attention. We will proceed to the next session. Thank you all.
Hello again. In this section, we will discuss about gas separation membrane. As you see in the previous lectures, in the most cases, we speak about the carbon dioxide capture, separation, air separation, oxygen purification, and others. And in this case, we can use the membranes, especially polymeric membranes. Today, the carbon dioxide capture and separation is very important because the increase of carbon dioxide concentration caused to the climate change and increasing of the world temperature. Therefore, there are many methods such as absorption, adsorption with different materials and different chemicals is used. But one of the very good processes is membrane processes. Why gas separation membrane is important? Because, as before we discussed, low hazardous material we used. In this figure, you see that the main used method for capturing carbon dioxide is amine scrubbers, absorption columns, that use the amine-based solvents for capturing, and this material is hazardous. But in gas separation, we do not use any additives. Only gas come, and before the gas stream, we have a filter cartridge for removal of particles resulted from corrosion of the tubes. And after filter cartridge, with using of a compressor, in liquid we have a pump, in gas transfer we have a compressor. With the compressor we increase the pressure, and we have a barrier that one gas more diffuse and another one low. And very easy method for separation of the gases from together. Low energy consumption and compact size. When you see the size of the scrubber column and the size of the membrane. Therefore, the membrane is flexible for design and need very low space and usually no corrosions. When we have solutions, the corrosions in pumps, in tubes is high, but here we know corrosions, and we also use the polymeric tubes if the pressure is low or temperature is low. Therefore, gas separation is very important, and in many industries, we want to separate 2 or 3 gases from together. For example, from natural gas, one problem in natural gas is the presence of acidic gases caused to the corrosions. And we must separate carbon dioxide and H2S from the methane. Or nitrogen removal. Presence of nitrogen in the methane increase the efficiency and heat capacity of the gases. Nitrogen is neutral, and when we want to combust the gas, the energy is reduced if the nitrogen is there. Therefore, nitrogen should be removed, H2S removed. Hydrogen recovery from ammonia in the ammonia process production. Carbon dioxide separation from syngas. Syngas is a mixture of monoxide carbon and hydrogen gas, as discussed in fuel cells. The separation is very important. Hydrogen separation used in the hydrogen storage, hydrogen fuel cell, as Dr. Laka discussed. And other many applications, such as monomer recovery. For production of the polymers, we first change the ethane to ethylene, and this reaction is not complete, and we have some ethane, we must separate ethane from the ethylene and recover for recycle. Excuse me. Recovery of different monomer from petrochemical companies is very important. Separation of the oxygen from nitrogen and many applications we can say for gas separation. The most gas separation membranes fabricated as a hollow fiber, because hollow fiber has a very high surface area and we have a high efficiency. But in some cases, we have also spiral wound gas separation, and we have also plate and frame. One companies in the world produce plate and frame gas separation models. The usual models you see, if we have a high temperature and high pressure, we fabricate the model from stainless steel. But when we have a low pressure, low temperature, we can prepare the models from a plastic based on the process. The material of the housing can be stainless steel or can be plastic. And this is a usual unit of the gas separation. You see that these are cartridge filter with different micron size. For example, 10 micron, 5 micron, and 1 micron. For separation of the solids from the inlet, because if we have one particle, only one particle can cut as a knife the membrane surface, and membrane will be destroyed. Therefore, in gas separation membranes and also in RO, very important, we have not particle in the entrance of RO and TFC membranes. Because in TFC membranes, we have a very thin layer, and thin layer can be cut with the particles. Therefore, we see we have a three cartridge filter with different pore size. If maybe we need to the heat, if we need to the heat, we increase the temperature, go to the pressure vessels, and separate the gas can to two different lines. And this is the real picture. This is the real spiral wound module fabricated from the Fuji film. Which now the Fuji film. What is produced before Lee? Camera. But we have only have a digital, and we do not buy the Fuji photograph slides. Therefore, the company is changed our products and changed from the photograph film to membranes, because in Bau's technique, the Fuji film produced films and changed the polymer for production of the membranes. This is a list of the membranes produced by different companies and the materials used. You see most is polyimide, cellulose acetate, polyimide, polyaramide. Aramide means that aromatic amide. And the application and the module type, hollow fiber, spiral wound, and one is plate and frame. Therefore, we can use for separation of the hydrogen from monoxide, hydrogen from nitrogen, methane, oxygen from nitrogen, separation of carbon dioxide from methane, and others. In the fabrication of the gas separation, we discussed 2 lectures about the fabrication of the membranes. Both porous and non-porous membranes can be used in the gas separation, but mostly use the non-porous one, and the mechanism is solution diffusion. But we have both porous and non-porous, and we have a prepared with a phase inversion, with the interfacial reaction, with the growth of the nanoparticles on the membrane surface, that we discuss all of these methods. About the mass transfer in the gas separation, we have 2 membrane type, porous and non-porous. If we have a non-porous, our mechanism is solution diffusion that we discussed. But if we have a porous membrane, we have the molecule size and pore size, okay? The interaction between the molecule and pore size and chemistry of the polymers membrane can cause different mechanisms. If the pore size is 100 nanometer to 10 micron, or when the pore size is bigger than 100 nanometer, we have no separation. We have no separation, and the mechanism is convective flow. That means we have a random diffusion and no. Therefore, for gas separation, the pore size should be lower than 100 nanometers. If the pores are lower than 100 nanometers, the separation efficiency is related to the mean free pass. Mean free pass of the gas. Mean free pass of the gas. What means? We show this schematic. In the mean free pass, we say that is the average distance a particle travels between collisions, between heat or between collision. That means this distance is mean free pass, average pass. This mean free pass is related to the size of the gas, and concentration of the gas, okay? When we have a big gas molecule, the distance will be lower. The possibility of the collision increases. With increase of the concentration, gas concentration, this can be increased because the collision increases. If the pore diameter is less than the mean free pass of the gas molecule, we can have Knudsen diffusion. Knudsen diffusion. Mean free pass less than the pore size. In this case, we have a Knudsen diffusion, and this mechanism most used in separation of oxygen from nitrogen from the polysulfone membranes, usually. And we have a very low selectivity, but we have. In the Knudsen diffusion, we have selectivity of 1.5, 1.6, maximum 3. 3 selectivity, that means oxygen 3 times more diffused from the nitrogen. Therefore, in this mechanism, in the Knudsen diffusion, in the surface diffusion, adsorption diffusion, we have very low selectivity, but very high flux. The porous membranes have high flux, low selectivity, but in diffusion, we have a higher selectivity, but because no porosity, the flux is low. For molecular sieving, mostly the pore size is extremely small. For molecular sieving, the pore size should be 5 to 20 angstrom, maximum 2 nanometers. If the pore size maximum 2 nanometers, in this case, we can have the molecular sieving if the pore size of two gas molecules is very different. We cannot oxygen separate from nitrogen, but we can separate butan from nitrogen, butan from hydrogen, because have very different molecular size. There are also another mechanism in the gas separation. In this slide, show that with increasing of the pressure, mean pass is very low, and by reducing the pressure in the vacuum, it is very big, and we want to big. But we need very vacuum condition, very low concentration, and it is not possible. Okay? We usually have a low vacuum in the gas separation, and in this case, it is based on the molecular weight of the gas can be different. We have I said that other mechanisms, such as capillary condensation. In capillary condensation, when we have a vapor, vapor is different from gas. You know, we say oxygen gas, nitrogen gas, but we say water vapor. That means with increasing of the pressure, water vapor can be condensed. Okay? Vapor can be easily condensed, but gas cannot be condensed in a usual condition. And for condensation, we must reduce temperature in very low critical temperature, and after that increase the pressure. Therefore, in this mechanism used for the separation of the vapor, in this mechanism, because we have a very narrow pores, when vapor want to pass from the pores, condense in the pores and change to the liquid, and in liquid, this valve cause to the blocking and filling of the pores. Therefore, we have a new barrier, and this barrier acts as a gas separation. This pores not act. Mostly this liquid condense in the pores cause to the separation. Therefore, we have also some mechanisms such as adsorption or mechanism, no here, such as surface diffusion. In the surface diffusion, we have some functional groups that can hopping the gas, give the gas from to one molecule, one functional group to another. And in this case, we can have this show. In this case, we have some functional group can increase the passing of the gas. Therefore, we have a different mechanism. I try to most say. About solution diffusion gas separation, before we discuss that we have two important parameters. First, the molecule should be adsorbed on the membrane surface, soluble in the polymer, and in the second should be diffuse. Therefore, we have a two-step, solution, diffusion. And we have a two coefficient, solution coefficient and diffusion coefficient. For some gas, diffusivity is high and solubility is low, or one gas maybe have a high solubility and high diffusivity. Generally, we have this equation for flux. When we speak about flux, we have a constant, permeability constant, and delta P as a driving force, and L as a membrane thickness. Okay, we before we discussed. This coefficient, permeability, is resulted from two coefficients, diffusion and solubility. And the selectivity is defined as the flux of gas A to flux of gas B. Whatever. We have the selectivity alpha A to B is to flux A to flux B. In the lab, we measure the volume of the gas passed. Okay, that means flux, this gas in which time pass, and our area of the membrane. Flux is related to the coefficient permeability, delta P and L. We test both A and B gas in the similar condition. That means delta P and thickness is similar. Therefore, we can use permeability A to permeability B, because the delta P can be removed from two sides. In gas separation papers, most of the students is confused about use of permeance and permeability. Permeance is the flux. Permeance is the flux of the gases from the membrane. And its unit is GPU, gas permeation unit. Okay? We say GPU, gas permeation unit. That is the volume of the gas passed from the membrane surface area in the certain time and in the certain applied pressure. Okay? This is the flux that in the gas separation we say permeance. Okay? And the unit is 1 GPU. This is the unit conversion. From the conversion of this unit together, we have this amount. Okay? The volume of the passage, for example, in 1 second, we say 2 centicubic gas passed in which pressure and how much the membrane surface. This is the permeance. But we have another unit as a barrier. As a barrier, not work. No, go to the next slide. That means barrier as present. I no discuss about this equation. Not go. Close and rind. Close from the slide. No work. Huh? No working. From your laptop, huh?
No, sir.
This. And rear. Okay.
The animation is 1 second, sir. I will go on.
What is this? Setup show. The online can be seen now. Need to restart, I think, huh? Yes. A barrier for each polymer and each gas is a constant amount. What means? In liquid filtration, I give to students a membrane and say that you test the flux. One student, the similar membrane, say that this flux is 100, and another student say that 200. And both can be true. But in gas separation, when two students test one gas separation membrane, cannot report different flux, different permeance. Because the permeability, the barrier of each polymer for each gas is constant. And we can find in the literature. We can find that this P box have carbon dioxide permeability of 12 barrier. If you report 13, in the paper will be rejected, your data is wrong. Because, okay. Because in the barrier unit, the permeance of a membrane in the gas can be changed because the thickness is not introduced. When you fabricate one student 10 micron, another 20 micron, the permeance will be changed, okay? But in barrier, the permeance divided to the thickness of the membrane. The thickness of the membrane is inserted. That means we report a film with thickness of 1 micron. This barrier shows that how many gas passed from this specific polymer if they have a 1 micron. You see, we obtained GPU 100. Our membrane thickness is 20. Okay? Therefore, we divide, we multiply this micron in GPU and obtain the barrier. That means we inserted the thickness effect. You see in this, we inserted the thickness effect in the reported data, and therefore we can report a different GPU, but we cannot report different barrier. If we report, we have a problem. In most cases, students come and say that I cannot reach two reported barriers. We have a commercial polymer and the gas, carbon dioxide, nitrogen. My barrier should be 10. I obtain 12. What is problem in most cases? In most cases, humidity. When the polymer absorbs the humidity of the environment, the polymer can be swell, very swell. And when we swell, we have some free volume, increase the free volume in the pores, and the flux increases. In this case, I say that keep your membrane in a vacuum oven for 1 day. And after 1 day, and before that, we give the membrane thickness. Before oven, the thickness of membrane is 20. And after 1 day in oven, vacuum oven, the thickness reduced from 20 to 17. Because absorbed many water, and this water have after that, give the similar barrier. As say, we have two solubility and diffusivity in the membrane, gas separation membrane. And we have a ceramic gas separation membrane. In ceramic gas separation, our mechanism is not send adsorption and others I discussed. But in polymeric membrane, if dense, our mechanism is solution diffusion, and this solution diffusion is related to properties of polymer and properties of the gas. One of the main properties of the gas is glassy and elastomer properties. We have the crystalline polymers, or semi-crystalline polymers, or amorph polymers that have their different behavior. In elastomer polymers, we have a flexible and amorphous polymer. That means we have 1,000 chains, and these chains can be moved easily together and is flexible. No hard interaction between the chains. But in the glassy polymers, we have a rigid and non-flexible and hard. That means we have a hard and strong interactions between the chains, and the movement of the chain is very, very low. And we have a crystalline behavior. That means we have a crystal units, and we have an interaction between the chains. Mostly when we have a hydrogen bond between the polymer chains, we have a semi-crystalline property. This crystallinity reduces the flexibility, and when we prepare a membrane from glassy polymers, we have a rigid pores, and the pores are not changed, the figures. But when we have an elastomer polymers, when a gas pass from the polymer chains with pressure, the pressure can be changed the pore size. And therefore, rigid polymers can good selectivity, low flux, but elastomer polymers have a bad selectivity, bad diffusion, and higher flux. We have a TG, glass temperature, and melting temperature. When we have a glassy polymers, such as this is rigid. But when we heat this in a temperature, this will be flexible, not melt. Melt is liquid. Not melt, but can change the form. The temperature that a rigid polymer can be deformed, it is the glassy temperature. That means in the bottom of high temperature, the polymer is flexible, and in lower than, it is glassy, such as glass and rigid. Therefore, the performance of a gas separation membrane is very, very related to the temperature. In a liquid membrane, with increasing of temperature from 25 to 30, no any change in flux, 1%, 2%. But in gas separation, the temperature is very important. With increasing of 5 centigrades, maybe flux 3 times, and rejection will reduce. Therefore, in test of the gas separation membranes, we should control the temperature. Only experiments, only our test equipment should be inside of an oven or should be immersed in water, as discussed afternoon. Therefore, we have a different behavior. The elastomer polymers in the ambient temperature, in the atmospheric temperature, is top of the glass temperature. Elastomer TG is minus 10 centigrade. That means in the 25 centigrade located in this area and have a flexible behavior. Based on this discussion, we have 2 parameters. Diffusion coefficient, you see in this axis, we have diffusion, and in the next slide, of course, we have a absorption coefficient. We have 2 different coefficients, and one discuss about. This diagram discuss about diffusion, not permeability, only diffusion, not solubility. In the diffusion, we have a PVC as a glassy polymer and natural rubber as a elastomer polymer. And compare the diffusion coefficient with van der Waals molar volume. That means when we go to the right, the molecular weight increases. We see when we have a rigid and glassy polymers, we have a better selectivity. The polymer, the membrane can be differ between 2 gases. For example, when we compare the hydrogen, our course about hydrogen, with nitrogen, the diffusion coefficient difference is about 100 times. Our diagram is logarithmic. The selectivity between hydrogen and nitrogen, this is about 2 and about 100 times. That means PVC selectivity for nitrogen and hydrogen is 100. But when we use the natural rubber, nitrogen here, hydrogen here, only we have a 10 times from diffusion view, okay? If we use this natural rubber, our selectivity is 10, but when we use this, maybe selectivity will be 100. Therefore, from diffusion view, the PVC is good. Okay? With help of these diagrams, we can select good polymer for our separation. Okay? But we see here that the diffusion of nitrogen is very higher than here. When the molecular size increases, the diffusion rate very sharp reduced. Therefore, the PVC or glassy membranes have a lower permeability but higher selectivity from diffusion view. This schematic shows that if our polymer is flexible, is elastomer, by passing of the gas, the chains can be changed our configuration and therefore do not good selectivity because the pore size can be changed. The free volume can be changed. But in the solubility coefficient, we say that the solubility coefficient is an interaction, not diffuse. In this case, with increasing of the molecular weight in both polymer, the diffusion is reduced because the lower molecule rapid diffuse. But in sorption coefficient or adsorption coefficient, the big molecules usually good adsorb. Where we compare methane with butane, methane have 1 carbon, butane 4 carbon. 4 carbon can better interact with polymer. Okay? We have this polymer, we have a 1 point for interaction, but we have a 5 point. When we have a 5 point, the interaction is high, and therefore the adsorption coefficient is high. And you see in this case, with increasing of the molecular weight, with increasing the size, the sorption coefficient increases. Okay. Also, say this with compressibility, and say that with increasing of molecular size, molecular weight, the boiling point increases. Methane is gas, ethane gas, propane gas, butane is liquid, paraffin is solid. That means with addition of the carbon to the molecular structure, the boiling point increases and the compressibility increases. When we have a pressure and we have a high compressibility, that means high boiling point, in the membrane pores, in the membrane free volume, the gas can be changed to the liquid and good adsorb. Therefore, in some papers discuss about compressibility and say that this is have liquid properties, but methane have gas properties. Therefore, this would easily adsorb, and therefore solution diffusivity is high. Therefore, we have a reverse behavior. In this case, where is the pentane? Here. Pentane have a very low diffusivity, but in this case, have a high sorption. Therefore, we cannot use these two diagrams separately. We can merge them, and after the merge, solubility in diffusivity. We say solubility in diffusivity is permeability. Okay? Okay? Forget, I come back. Here we say that permeability is diffusivity and solubility. Everybody is hungry. This is a diffusivity, and this is solubility. Therefore, this is the sum of solubility and diffusivity as a permeability. In handbook, in gas separation handbook, we have these diagrams for all all polymers. Okay, when we have a thin film of polymers, no porosity, we can use these diagrams for prediction of the permeability. And therefore, when we have, this is the polysulfone, in the temperature is very important. You see the temperature. With change of the temperature, this data is changed. Therefore, there are tables, the permeability change with the temperature. In this temperature and with this polysulfone, the permeability as a barrier is this amount. And we cannot report another data. If we cannot, our paper is rejected. Okay, with having of this, if we want to separate the methane from nitrogen, we see that polysulfone is not good because have similar permeability, and therefore we have not selectivity. But if we want to separate methane from nitrogen, we see that the PDMS is good. Therefore, we can use of these diagrams predict the separation. You see in these diagrams that the most permeable gas is water. When we have a mix of the gases, the water will be passed rapidly because both good condensability and have a very small size. Therefore, when we have a mixing of the gases, first the water will pass. For glassy polymers, we have this behavior: helium, hydrogen, ammonia. See here, monoxide is big or carbon dioxide. Monoxide is big or carbon dioxide? Carbon dioxide is bigger, but carbon dioxide has rapid diffusion because have two functional group. Monoxide, one interaction place, but carbon monoxide have two interaction. Therefore, solubility parameter of the carbon dioxide is higher than the monoxide and have a higher diffusion rate. Okay, I pass. The reported selectivity for the different gases. In the lab, we mostly test the gases separately. We have one membrane, first pass carbon dioxide, and after that we pass nitrogen and obtain the permeance and calculate the permeability and others. But in the ideal, we have a mix of the gases. Why we do not use the mix of the gas in the lab? Because the measurement of the mix of gas need the gas chromatography, and in many labs, no gas chromatography. Therefore, report the ideal selectivity. But when we have a real selectivity, we see that when we have a mixture of the gases, the gas could interact with together and one gas when adsorbed can block the active sites. And therefore, we see that the selectivity for pure gas can be changed in the presence of the other gases. But it is better we mix the mixed gas for true data. But for report of the barrier, we use the pure. But for report of the selectivity, it is better we use mix of gas. In the liquid membrane filtration, MFUF and other, we have a fouling. That fouling causes to the reducing of the performance. In gas separation, we have also the fouling. But usually do not say fouling. In this case, say aging or plasticization. The similar to the fouling, the selectivity and permeance of the membrane change during of the time. One property is plasticization. Plasticization, that means that we, in the first new membrane, we have this structure, this compaction. After 1 year, because of some impurities, some adsorption of gas to the polymer chains, the free volume between the chains is changed. Between the chain is changed. Okay? Change. And therefore, we usually that after the certain time, the flux increase. The flux increase and the selectivity reduce. After this time, 2 months, 3 months, 1 year, we say that the membrane have plasticized and changed the properties of the membrane. The membranes will be brittle. Membrane was flexible relatively, but after 1 year is very brittle and the properties is changed. With addition of nanomaterials, in this case, increase the long life and reduce the plasticization. The insertion of the nanoparticles can interact with the polymer chains and do not allow to interact with the gas. Mostly carbon dioxide causes to the plasticization. And another is aging. In the aging, we have a reduce in flux. Reduce because when we use the polymer as a thin layer and we have a pressure, in the gas separation, we have in most cases high temperature and high pressure. This compress the polymers during the time, and after 1 year, the pores and the free volume reduce to this one and cause to the reducing the free volume and the flux. And in this case, you see after these hours, the membrane is brittle and destroyed. And as a final slide, in the gas separation, we have a Robinson boundary or Robinson bond that shows the barrier and selectivity, permeability in selectivity. We now, with increasing of flux, increasing of permeance, the selectivity reduces. And we have seen that we have this bond. This one is the previous or old Robinson bond, and the right is the new Robinson bond. When we research in the lab, the best membrane is that located in the right of this bond. If we prepare a membrane and have the selectivity and barrier permeance, and our membrane based on this selectivity and permeance, if located here, it is not good, will be rejected. Because say that your membrane should be in the upper of this band. This blue locations is good. If we can prepare a membrane with high flux and high rejection, this area is ideal, is very good. Therefore, in the gas separation, most of literature you see reported here, this is a very bad, low flux, low rejection for carbon dioxide from methane. And we have these Robson bonds for different gases, for oxygen, nitrogen, carbon dioxide, hydrogen, and others. This is also the similar diagram for reverse osmosis membrane. The rejection of reverse osmosis related to the flux, and we have a good membrane should be located in this area. There are new polymers in the fabrication. In the previous slide, you see traditional one, but every day new polymers synthesizes and report for fabrication of the membranes, such as polymers of intrinsic microporosity, which is very important and have a very high flux. That means there is some free porosity, microporosity, in the structure of these polymers. You see, this intrinsic, we have some free volumes in the polymer structure, and these free volumes increase the flux. Okay? And this is a very expensive polymers for research. Thank you. I don't know. Have any question? I will rapidly discuss about the gas separation. It's a very interesting area, but need a good equipment for testing of the membranes. Everybody is hungry.
So it was very nice, and I'm sure the students, they had all their questions answered. That's why they did not ask anything. And that we'll see, they will test it tomorrow. Do not worry how much they understood. Anyway, thank you so much for your lecture. And so please join us for lunch in 312. The lunch is ready. And we'll meet after, so what is the time now? 1:45. So we'll meet around 2:45. Okay, after 1 hour. Okay. Thank you so much.
Thank you. Thank you. Very good. Again. Start. Okay, I will. What is there? Good evening. In this tutorial, we will speak the setups that used in the testing of the membranes in the lab scale. And I try to show some this apparatus. You know that the flow regime on the membrane surface can be in dead end model and in cross flow. And as discussed, in most industrial application, we have this regime because the fouling in this scale is lower. But in lab scale, in most use the dead end system for testing of membranes, because if we want to use the cross flow cells for fouling test, we should today's test membranes for fouling. But in dead end, with 1 hour, 2 hours, membrane mostly fouled and flux reduced, and therefore we can rapid test the membrane, and the fouling ratio, fouling amount in the dead end is very higher than the cross flow. And if we have a good flux recovery ratio in dead end, we can see we have very, very better performance in cross flow. For dead end test of microfiltration, all of porous membranes, we have these similar cells. You see, this is the open of this cell. This cell have 2 sections, bottom and top. This is top section. This is bottom section. And you see, we have an orange, elastic orange for sealing. We get out this orange and put the circle membrane on the surface of this porous medium. This is a Zinter filter. Zinter. We have a very big pore size and usually used as a gas filter. In some valves, entrance of valves, this Zinter filter is a support for only keeping of the membrane. We put the membrane here. We put next this tubular, that this tubular here is from plexiglass, from a plastic, but for high pressure we can use the metallic one, stainless one, and put this section on the top of this, and these tubes go from these pores, and we close them, and we have this. We have a styling. We have a magnet inside of this part, and we put the dead end cell on a styler, and this styling remove or reduce the concentration polarization. We want have a real conditions for test, and this agitation, this stylation, reduce the concentration polarization. This magnet come 1 centimeter top of the membrane and mix the direct top of the membrane. This is a general cell. We have a gauge, pressure gauge, for showing of the how many pressure applied, and we have a tube that the entrance of the feed. This is connected to another tank, and usually here have 100 to 300 milliliter volume. We have one feed entrance, and we have a permeate entrance. Permeate here collected from a beaker or cylindrical device. There are different forms of these cells. As you see, all of can be plastic, or here plastic, here metallic. This is a schematic of the setup. The dead end cell is here located and connected with a tube to the main tank. And for applying up pressure, we usually use the nitrogen tank. Have a regulator that can reduce the pressure and apply 1 atmosphere, 2 atmosphere, usually up to 10 atmosphere. We use this device up to 10 atmosphere test. And the permeated can be weighted or can be volume is measured. This is the usual schematic of a dead end setup. This is another picture. Here, the main, in the previous slide, the next slide, we can see that some cases the main tank can be steel, stainless steel, or here have a plexi and come here, measure the pressure and the permeate collects on the balance. This is all steel. This all steel and used for high pressure, and this is the styrene magnet. Or here you see that for continuous measurement, the balance is connected to a computer and no need to student stay here. After preparation all of things, automatically weight the collected permeate. You see, both the tank, stainless tank, is connected to a cylindrical. We can use, instead of cylinder, we can use a compressor. We can increase the pressure with compressor and no need to nitrogen. These are my setups in Iran that have a, because the error of membrane is high. And for reporting of one data, we usually give average of 6 tests of membranes. After giving of the 6, we give the average and report data. Therefore, very time is needed. For reducing of the time, 4 membranes in a simultaneous time test for increasing of the efficiency of the group. Or in this case, you see, one student work with this, another with this, and test the membranes. Another setup is cross-flow. We use cross-flow mostly for RO and nanofiltration membranes. If we have a low pressure, use the plexiglass one or polyethylene one. If we want to test organic resistance nanofiltration, that we separate some pollutants from solvents, organic solvent. In this case, the material is PTFE, polytetrafluoroethylene. This is for RO, for high pressure, 50 atmosphere pressure. In this case, we have a very secured system. In the cross flow, you see in the dead end, we only have a feed and permeate. But in the flow, in the cross flow, we have a entrance for feed, permeate, and concentrated. Okay, one feed come and divide to two stream, one concentrated and one permeate, and we measure the entrance pressure and exit pressure and give average for reporting of our applied pressure. When we say our pressure is 10 atmosphere, this usually is 10 point. This is the 9.5. 10.5, this is 9.5. Usually we have a pressure drop in the system. Therefore, the entrance and exit is difference. This is a graphical design of the cells. You see that the cells have two parts, bottom and top section, and the membranes is located in this area that show that feed come here, pass from the membrane surface, and as a concentrate go to the tank. And for sealing, we have a two O-ring that seal the membranes. This is a simple test of the cross flow. This is our cell. One here is entrance of the feed, and this is go to the concentrate. And we have entrance pressure and exit pressure, and with control of these valves and these valves, we can control the flow and pressure. When we want to control the flow and pressure, the pump is began to work and circle the water, but with closing of this valve, we can increase the, when this valve is completely open, we have no pressure. When we begin to closing, the pressure increases, and this is a bypass, and with this bypass, we also control the flow of the membrane, flow of the fluid that pass from the membrane surface. This is my cross flow setup in Iran, and you see for repeating and increasing of tests, we have three parallel cells for continuously test of three membranes. You see here, we have a high pressure pump. Here is the tank. We put feed here. From this tube, go to the pump. The pressure increases and insert the first cell, second cell, and first, second, and third cell. And in each section, we measure the pressure for controlling the pressure. This electrolytic system can cause to the increase of the pump rotary, and we have a temperature control. This is the temperature system. We have a cooling system in the tank. With working of the pump, the temperature of the feed increases, and for reducing of the temperature, we have a stainless steel foil that entrance cool water and decrease the temperature. Therefore, in feed tank, this tube you see, cool water come and hot water go. Therefore, we can control the temperature. The cross-flow systems, our cells, this cells is a what you say to for angle? What is? Not circle. What is this for in English? Rectangular. Rectangular. But some cells can be prepared in circular form, as seen. In this area, in the rectangular, we cut, for example, mostly 4 in 10 centimeter. But in this circular cross flow, we cut as a circle, and here is entrance of the feed, and here is exist of the feed as a concentrate. And when here entrance, go to the all of the circle, and in all of the area can come to this central tube. Therefore, we have a cross flow on the membrane surface. This is a clamp for keeping them together and obtaining them. Some circular cells also, the effective area can be rectangular. This is also another cross-flow system. Osmonics setup system is very expensive, this one. And this another schematic in lab with rotometer. This is a rotometer for measuring the flow. Another pressure cell, another. Oh. Is there any question about dead end and cross flow? Everything obvious? It is possible, no. I want to draw a figure. It is possible this go to the top, I write here. This go. I want use this. This go to the top, can collect.
Actually, what happens that it will not record, no? It will record.
Cannot sound?
Actually, what happens, their camera resolution will not be very
Okay.
good if we write. So
Okay.
what you can write, sir, on the white part?
I wanted
to
to-
give you a slide.
One second.
Thanks. You can write it.
Okay. I want this here. Okay. Thank you. For membrane test, for example, we want test a UF membrane. After preparation, we have a 4-step test for membrane. We first measure the pure water flux, how many the flux of this membrane, and in the second, we usually fold the membrane for showing that this membrane, how can be fold. And after that, we measure the recovery of membrane. This membrane, how recover there after falling. And we use the washing for the membrane. And in the 4 steps, we test the rejection ability. rejection ability for protein, for dye, for heavy metals, and our target pollutant, okay? Therefore, we have usually this diagram. You see in more papers that this is a time and this is the flux, okay? First, we measure the pure water flux. For example, this is the 2 hour. In different time, every 10 minutes, based on the membrane flux, 20 minutes, we measure the volume of the water, and we know how membrane surface, and with measuring of the volume and area and time, we report our flux is here with pure water. Here is pure water. Okay. In the second step, we replace the pure water with foulant agent. Foulant agent can be oil based on the wastewater, can be our wastewater. We have a industrial wastewater and replace our pure water, distilled water with our wastewater. The standard solution is bovine serum albumin. Bovine serum albumin, a protein from cow, BSA. In the most cases, for comparing our results with literature, we must use the BSA with this concentration. What happened? With this concentration, when we put the BSA in the dead end cell or cross-flow cell, BSA attaches to the membrane surface and reduce the flux. We have this, rapidly reduce. And we usually test 1 hour, 2 hours the BSA. This is the BSA flux. With a standard solution mostly, but we can use other foulant. And after 10 minutes, 20 minutes, we reach to the stable one, okay? Now, we separate the membrane from the cell and wash only with water. Only with water. We want to say that our membrane, how is resistance to fouling? How can recover their properties with washing? We usually do not use the cleaning agents such as acid, base. Water. After washing, 20-minute washing, usually with water, we measure the membrane, pure water, second. We say second. Second flux. Okay? Second flux. With this data, we can calculate the membrane intrinsic resistance, membrane resistance to gel layer, membrane resistance to pore size fouling, and others with this simple test, okay? If our membrane is very good, this flux should be here. This show after falling and cleaning, the ideal membrane is that this come to here and go this. But our membrane have not complete recovery. We can calculate the amount of recovery. We name this one as G1 protein flux and G pure water 2, okay? Now we can calculate the parameters, which is one is the sealer. No. We have the first question. We test the membrane with pure water, okay? Why flux reduced? During the time, our flux reduced to this one. Is there any foulant in distilled water? We have tested the membrane with only pure water, distilled water, no salt, no any. Why flux is reduced? That means the membrane is followed. Why happen? Due to the compaction. Due to the compaction. Oh. When we apply pressure, membrane began to compaction. Oh. For reducing the compaction effect, we before this point, we usually test the membrane with pure water with higher pressure. If our applied pressure is 2 atmosphere, before beginning in this area, we apply 1 atmosphere higher pressure. If our applied pressure is 2, we use 3 atmosphere for 30 minutes for compaction, good compaction. After that, reduce the pressure to 2 and start this point. But we have now the compaction, and this compaction is every time. After 10 days, maybe reach to the stable, but we see that here is sharp, but reach to the steady state. Therefore, after that, we have a compaction. After this one, we can calculate the fouling parameters, FRR, flux recovery ratio, that is the flux of second pure water to flux of the first second. If the flux of second and 1 is the same, we have 100 FRR, that it is ideal. We cannot reach to this usually, okay? We have 2 fouling parameters also as a reversible fouling ratio, reversible fouling ratio, and irreversible. Okay, fouling ratio. reversible with test of the protein, okay, the pressure is reduced, the flux is reduced, and after washing, this amount is recovered, reversible, okay? This amount is reversible. This amount I show with other color, maybe. This amount is reversible. But this amount of flux is irreversible. Therefore, we can calculate the amount of reversible and irreversible that calculate as this. G dou minus GP to G1. Irreversible, this amount GW1, GW2 to G. Okay? And there are another equations that I will speak tomorrow in the following section. We can calculate intrinsic resistance, cake layer, and pore resistance, and others. Usual test with UF, MF, NF is this test in the lab with the shown setups. And in every test, when we want to measure the salt rejection, dye rejection, every rejection, we first compact pure water flux, and after that, we use the separation, heavy metal solutions replace, okay? But we have two series, one series for BSA fouling test, and second for separation test. Okay. We can go to the slide. For hollow fiber test, the process is similar. In hollow fiber test, we can also test as a dead end and as a cross flow. We have this usual setup for hollow fibers, you see, such as this also, you see. We can prepare from stainless or from the plastic tubes. That, for example, the feed can be here, go here, and as a concentrate, get out, and the permeate can collect here and here. In this case, we have a cross flow. Feed come and concentrate. But if we close this exit here, we close, we only have a feed and only permeate. Therefore, when we have an open here, we have a cross flow. When we close the concentrate section, we will have a dead end section. Such as the flat sheet setups, we have a permeate tank, we have a feed tank, and usually we use the peristaltic pump for applying the pressure. This shows the flow of the this solution. And here we can see the applied pressure. For ceramic membranes, also we prepare this similar to the hollow fiber modules, only we have a one tube here. Okay, we can plastic tube or ceramic tube. For sealing, we have an O-ring, the similar one. The feed come here and exist from as a concentrate, and the permeate can be go here or reverse. Feed can come here from concentrate, and we collect the permeate in this case. That means the feed can be outside of the membrane or can be inside of the membrane based on the active layer of the tubular membrane. This is a setup of the ceramic tubular membrane with a length of 1 meter. We have a pressure gauge for entrance, pressure gauge for concentrate, this valve for control of flow, and here we collect the permeate. This is a tummy ceramic membranes that sell 10 membrane with a pressure vessel. You see, this is a pressure vessel, and such as them, we can put the membrane here, add the black O-ring here, put them with this clamp, and test the membranes. One of the important parameter in the filtration membrane, MF, UF, and NF, is molecular weight cutoff. Molecular weight cutoff measurement. For measurement of the molecular weight cutoff, we usually use 5 or 6 different molecular weight of a component, such as polyethylene glycol, such as starch, such as dextran, such as glucose, saccharose, and others, okay? For ultrafiltration, we use the big size of the polyethylene glycol. For drawing of this diagram, we need at least 5 and 6 points. For example, this kilodalton, we select polyethylene glycol. Polyethylene glycol have a molecular weight from 200 to 2 million Dalton. Okay? Therefore, we first select one solution and see that the rejection of this molecular weight is low. The second molecular weight, the third, 4, 5, 6. We 6 times test our membranes with different molecular weight solution. If we have a HPLC, we can mix all polyethylene glycol with different molecular as a one solution and measure. This is very easy, but usually we have not HPLC. Therefore, we test separately so we have prepared 6 different solutions and began to test the membranes. With having of these 6 points, we draw this diagram. For measuring of the molecular weight, we see that the points can reject 90%. Therefore, after drawing of this diagram in the Excel, we draw this line to the cut the diagram and go back to this one. And this place will be our molecular weight cutoff. if we go to the commercial membrane sites, you see that there are maybe 20 ultrafiltration membrane with different molecular weight cutoff. Say I have a UF with molecular weight cutoff of 50,000, 100,000, 200,000, and this molecular weight cutoff is showing the pore size of the membrane, and it is reality than the other processes that yesterday I discussed. This is a real test. You test with a solution and obtain this data, and this is very real. Another setup is dialysis or forward osmosis membrane, or membrane distillation membrane also. In forward osmosis, membrane distillation and dialysis, hemodialysis, we have the solution in the permeate site. In the UFMF, as you see, in our setup, the permeate goes to the weather. But in this membrane processes, we need two pumps instead of one pump because we have a two stream. One stream as a feed, one stream as a receiver. Receiver in the permeate size. In dialysis, hemodialysis, membrane distillation, we must have a flow in the permeate site. Therefore, you see, we have a two pump, two tank, and if this tank is feed, come to feed site and get back to this one. Okay? And for this one, we have a pump. Therefore, one pump is for feed site and one pump is for permeate site, as you see in this schematic. For MF membranes, for separation of oil, water, we usually, the best membrane is gravity-driven membrane. That means in this scale, we have not pump. Only with low pressure, now, when we have a 1 meter height of water, 1 meter, this is equal to 1.01 atmosphere. 10 meter water is 1 atmosphere. Okay, you know. Therefore, in this height that is mostly 30 centimeter, not very high, with very, very low pressure, gravity-driven pressure, due to we have a very big pore size. For example, if the membrane is hydrophobic, oil pass and water not. If the membrane is hydrophilic, water pass and oil not. In the YouTube or in the supplementary information of the oil-water separation membranes, you can see many videos that pour the water here and rapidly oil separate from the water. For testing of this, we usually have a similar setup. If we need a little vacuum pressure, this is can be connected to the vacuum also, if we want to apply very low pressure. Membranes are located here. This section separate from membrane located here. You see this membrane, and this clamp keep the membranes. This is a MBR, membrane bioreactor system. In the MBR, we have a activated slot tank. that there is a microorganism there, and we give oxygen, aeration for biological degradation of the organic pollutants, and give some foods, some vitamins, some ingredients such as zinc, magnesium for growing of the microorganism, because microorganism is live and need food. Without carbon, need the mineral also. For separation of the microorganism from treated water, we usually use immersed microfiltration or ultrafiltration. Usually similar setup is used. You see have some suction pump. This is yellowish, usually filled with the aeration tank. And maybe we can have anaerobic, without aeration. This usually aerate, and with usually non-aerate. I have a video we can show. Let's show video. MBR system. This is a MBR system in a Turkish lab. We have a feed tank and permeate tank. This is a control system. Aeration of the sludge, and the membrane is immersed. Them and suction can take with this valve. We have a, please repeat again. We have a 3 pump, 2 pump for feeding, 1 feed, 1 not other minerals for growing of the microorganism, and 1 pump is for suction of the membrane. Okay. The second film, dead end, no, video. Dead end. This is one of our in Iran for parallel. This styling reduce concentration, polarization. And the permeate come from this blue, the applied pressure, 3 atmosphere. And we measure the volume with this cylindrical. Okay. In some cases, we need to measure the diffusion of a molecule or ions from membrane, and measure that this membrane how diffusion efficiency is dialysis cell most used. In this case, we have similar system that membrane is located here, and with this clamped or closed, and one side is feed side, and other side is receiver side. We put feed here, and after our every certain times, sample from the receiver side and measure the concentration of diffused ions. If we have a salt, measure the conductivity. If we have a molecule, we give the TOC, COD, or UV spectrophotometer for measuring. Therefore, this is a diffusion systems used in forward osmosis, dialysis, membrane contactor, intrusion membranes, and others. This is also another one. We usually locate this device on the stirrer, and we have a styling for uniform dispersion. Therefore, these systems located on the stirrer surface. Another system is gas setups. For testing of the gases, there is two methods. Say constant volume, constant pressure. We have a two method for testing of the gas. Constant pressure, constant volume. Constant pressure, that means we apply, for example, 5 atmosphere pressure in the feed side and measure the flow of the gas, such as the liquid membrane. This is named as a pressure constant method, and usually the flow of the gas can be measured with bubble flowmeter. In bubble flowmeter, this tube will connect to the permeate of membrane, and we have here a soap solution. We pressing of this, one of the soap bubbles come here, and the gas carrier the bubble. When reach to here, that is reach to here, that is have a number 0. Reach here, we began the timing, and this bubble go here, and after reach to here, we measure the time. For example, for passing of 10 milliliters, we need 10 minutes. And with giving of the volume and the time, we obtain the volume of permeated gas. This is a simple method. We have digital one of this, digitally measure and report as a number, and different time. This is the pressure constant. And the second method is volume constant. The data of volume constant is better, and in the most cases request to report volume constant. In this method, as you see, all of system is located in water. Because I say that in the gas separation membranes, the temperature is very important. And we locate all of the system immersed as a water, and we control the temperature of water. Or we can locate all of systems in an oven, such as this. In this setup, we have an oven, and all of these systems located in this oven, because temperature is very important. With change of 1 centigrade, the permeability will change. The membrane is located here, and we have a tank here in our system, in Iran. And we can have different gas, methane, nitrogen, argon, oxygen, every gas. And the capsule is connected to this tank in the water, and the temperature controller, and come here. And in this cell, we have a membrane. We located the membrane. And these blacks are pressure transmitter. All our pressure is measured, and we can see in this plate all of the pressure and temperature. Okay, after passing of the gas in the constant volume. We know the volume of this section, and you see we have a very narrow tube. This is narrow tube. Because the permeate is very low, our surface area is 3 centimeters. Therefore, we use very narrow tube, very small diameter tube, that we can, our system was sensible. And with the pressure is constant. No, the pressure here is constant, but pressure here is this 0 time is 0. And with increasing of the permeate, the pressure began to increase. And we measure the increase of pressure in the permeate side. And all of systems is connected to a laptop, and we draw the change of permeate side. Also, as you see, in this setup, we have a left system and right and left. You see better. This is the permeation measurement. This is for measurement solution coefficient, adsorption coefficient. In the previous lecture, I said that in gas separation, solubility and diffusivity is important for measuring that this polymer, how like to adsorb these gases. We have this system. In this system, we have a very little dish, usually 1 gram polymer we put in this dish and locate in this system and contact with the gases. For example, very low pressure gases, for example, this, right? Locate 1 gram polymer in contact with 0.5 atmosphere, for example, carbon dioxide gas, and give time, 5 hours. And the polymer, if good had interaction with carbon dioxide, began to adsorb the gas from the gas media, and therefore pressure reduced. After reaching to constant pressure, we every hour check the pressure. Pressure reduced to after constant condition, for example, reached to 0.3. That means 0.2 atmosphere carbon dioxide was adsorption to 1 gram polymer. Therefore, we can calculate the capacity of gas adsorption on the membrane surface, and there are some equations. We can calculate solubility diffusion. In this system, we measure permeability. In this system, solubility coefficient, and from minus of the solubility from permeability, we can calculate diffusivity coefficient. Okay? Therefore, we calculate both solution and diffusion coefficient. This system is simple, but gas test is very expensive. The liquid test is easy. But this system, I say very simple, but you see not simple. Every of this transmitter is expensive. All should be steel, stainless steel, and others. But this gas setup is in a petrochemical company. I have a big project with them and fabricate this setup for mixing of gas. We have a different pressure gauge, different mass analysis setup for measuring the mass flow, and very, very expensive setup this for gas separation. Thank you. We have a video, show the video, and our presentation finished. If any question about the setup? We have a pervaporation setup, membrane distillation setup, dialysis setup, bigger one, but no time to show. We have a minute. A video, please. Video. For showing the entrance of the gas setup. Yes, gas. The video of this gas. This is better, huh? This is the water tank. These valves is used to vacuum. Before testing, after keeping the membrane, we vacuum the system for zero pressure in the permeate side. After the vacuum, we began to test. From capsule, the gas come here for control the temperature, and next come to the entrance of the membrane with opening of this feed valve, feed pressure. This is the cell, and this is the for vacuum. This is the permeate side. Permeate side come here. We have a very little tank here, and measure that. This is a very sensitive pressure, and if during test here we have, for example, 5 atmosphere. If during test the membrane is tear, is poor, this transmitter will be destroyed. Therefore, the membrane should be very good stability. If no stability, because very sensitive, this sensor will destroy. This is, we have a 2 O-ring for sealing of the system. The effective diameter is 3 centimeters because the gas polymer is very expensive. We do not test the big one. We want to use the lower amount that reduce the expense of experiment. This is the adsorption. We have a very little dish. We put the 1 gram polymer here and put them in this one. Control of temperature, heat the tank, feed tank of the water, and this circulation pump circle the water in the system for controlling of the temperature. Feed pressure, permeate pressure. This is sorption section, feed sorption and downsorption. If any question, please. Electric system. We have a USB. This USB can be connected to laptop for recording of the data. All measured pressure can be recorded in a laptop. Thank you. Any question?
Any question from the audience side? No question? Okay. All the videos and the explanations that you were saying, it was very fascinating to me, especially about the gas separation. So these were very exciting. I hope some of us will get a chance to work on such kind of systems on by hand in the near future. So I thank the professor for his enlightening lecture today. So next, what we have is a tutorial. It is about some practical problems as per the schedule, some practical problems related to the membrane filtration setup. Okay. So shall we take a 5-minute break and start, or shall we start right away? Break? Okay. So let us have a 5-minute break, short break, and then we will gather back here to restart the session. Not this one, sir. Not this one. Tutorial. That one only. That one only. That one only, sir. Tutorial. Yes. Yes, yes, this one. This one. Hello, good afternoon. Shall I start? Okay. So, a very good afternoon to all of you. So, today in this session, what we are going to discuss is basically some practical problems, numerical problems basically. Whenever we are talking about application of many field, application of various film or membrane type technology in our various application sector. So then whatever theories and the calculations are involved to predict the permeability or predict the performance of the membrane. So we are going to look into some basic aspects of that in this session. Okay. So over here we are going to solve, or we are going to see a few situations which are very close to real life. So the first situation is giving us, telling us that you have to separate 4 kg per meter cube of a protein solution. So in the previous session we were talking about BSA filtration. So take an example of that we are filtering a BSA solution having a 4 kg per meter cube and you have 96% observed retention. Now they are saying that film theory is valid. Now what is film theory? Whenever we are having any porous membrane, then we in order to predict the flux, or in order to have an idea about what the flux is going to look like, for that we have a formula like given like this, that J is equal to K into ln into Cm minus Cp divided by C naught minus Cp. So this is the formula that is proven by equating the flux in and around, in and out of the membrane. Okay. So this J is the flux and K is the mass transfer coefficient. Cm is the membrane surface concentration. So whenever we are having a membrane filtration, some component is being rejected by the membrane, some component is being rejected by the membrane and without PowerPoint. Yeah, so actually that might be a better solution, obviously. So if we have a rejecting membrane, then we have a build-up of the contaminant layer over the membrane surface. So just beside this membrane surface, we have the concentration is Cm just over the membrane surface. The concentration on the bulk is Cp. So the concentration in the bulk is C naught or the bulk surface concentration, and when the permeate comes through, on the permeate side the concentration of the contaminant or the protein for us will be Cp or the permeate side concentration. Okay. So now observed retention or percentage rejection is given like this, that it is actually the amount of protein that is being rejected by the membrane. So that if we have to create, so originally we have how much C naught and finally how much it is permeating through the membrane, Cp. So this much concentration has been rejected by the membrane, and that if we divide it with C naught, then we get the rejection. So this in percentage will be given by this is basically for us, this observed retention is going to be 0.96 as per the problem statement. Okay. So 0.96 is the observed retention, and C naught is the bulk concentration, which is given by 4 kg per meter cube. So if now we put the values here, we will get that the Cp or the permeate concentration is equal to, if we solve this problem, this equation, we put the values, we will get Cp to be 0.16 kg per meter cube. So this is what the Cp or the permeate concentration will be given like. Now in order to get the flux, we also will be needing some other factors like K. So in order to get the K, we have some empirical relations which is very popular or very widely used in chemical engineering, and that empirical correlation is given in this problem statement itself. So using this empirical correlation, what we can determine is that this Reynolds number into Smith's number into dE by L. This basically Reynolds number is d into u naught rho dV by mu, okay, and mu by rho d is your Smith's number. So if you multiply them, the only term that remains for this is that, so Reynolds into Smith's number. So Reynolds will be d into u into rho by mu into Smith's will be mu by rho into d. This d is the equivalent diameter and this d is the diffusivity for you. So they cannot cancel out, but this mu and this mu can cancel out, and this rho can cancel out for us. Okay. So if we have this analysis, then we can, and Sherwood number is, this Sherwood number has a definition like this. This Sherwood number is K into L by D, where this K is your mass transfer coefficient. Now if we put the expression of the Sherwood number and Smith's number here, we will get that our K is equal to 8.31 into 10 to the power minus 7 that 8.31 into 10 to the power minus 7 into L to the power minus 1 by 3, or L to the power 0.33. That will be your K, expression of K. Now if we put this value of K inside our film theory equation, the combining these two into this equation, so this is your equation number 1, this is your equation number 2. So if we combine equation 1 and 2, you will get that your J or your flux will be equal to 2.71 into 10 to the power minus 6 into L to the power minus 0.33. Okay. So this will be the value for J in our case. Now why we are interested to get the expression for J? Because in this problem statement they are telling that your filtration rate is 100 liter per day. Okay, 100 liter per day is the volumetric flow rate. Now 100 meter per day is the volumetric flow rate, and the area for us will be the width into L. So that will be, in this case, the width is given as 0.04 centimeter. So area is equal to 0.04. So I think the problem lies whenever we are trying to put a point here. So 0.04 into L, that will be your area. Now J into area is nothing but your volumetric flow rate. So given this, if we combine this equation 3 here using equation 3, we will be able to solve for L, and that will be coming as around 35 meter. Okay. So for getting a solution of this situation, the length of the membrane that we need is around 35 meter. Okay. So this is practically this is one of the application of film theory or a typical chemical engineering fundamental problem from this. So where we can effectively determine that if this is your permeate concentration, this is your membrane surface concentration, then how much of the length that you require for this type of operation. Okay. So is there any question, any doubt from this problem statement or any situation? No? So let us consider or move to our next problem. In this next problem, we are going to use one famous equation called Darcy law. So how many of you are familiar with Darcy law? Come on, many of you I think. Yes. So you should be very, very familiar with Darcy law, and this Darcy law is practically very simple. It is practically giving you a relation between your flux and the driving force that you are applying. Okay. So let us have a look into the problem statement. Here in this problem statement, we are also talking about the osmotic pressure. So what is the osmotic pressure? Whenever we are having a concentrated solution or a contaminant solution present in our solution, so they themselves exert a pressure which acts in the kind of a neutralizes or kind of acts in the opposite direction of your delta P. So that is our osmotic pressure. So this problem talks about that osmotic pressure in this case. It is a macromolecular solute which is basically protein, ultrafiltered through a membrane at a fixed temperature. Solution concentration is 0.015 molar, 96% rejection is achieved. If the feed side pressure is 4 bar and the downstream pressure is 1.1 bar, calculate the effective driving force. So in the first problem, we are going to neglect the concentration polarization. In the second situation, there will be a polarization modulus of 5.5. So what is polarization modulus? Polarization modulus is nothing but the ratio of Cm and C naught. So the membrane surface concentration divided by the bulk concentration, that will be giving you the polarization modulus. Okay. So effective driving force, as I was telling that you have a delta P and your pi or osmotic pressure, this actually works in opposite direction of your delta P. So effective driving force will be delta P minus delta pi. Okay. Now what is delta P? Delta P is the pressure difference between the feed side and the permeate side. Now in the feed side, how much pressure we have? Feed side or the upstream side? 4 bar. In the downstream side, we have 1.1 bar. So the delta P in this case will be 2.9 bar. 2.9 bar. Okay. bar will be the actually delta P. Now, in order to have a delta pi, in this case, what we need is that we need the osmotic pressure on the membrane side and we need the osmotic pressure on the permeate side also. Okay. So now for any solution which is very much dilute in nature, the pi or the osmotic pressure is given by one simple formula which is given by famous scientist called Van 't Hoff. that pi is nothing but R into T into C, where R is nothing but your ideal gas law. So given these equations, given these formulas applied, Van 't Hoff correlation, given that our delta pi we can calculate, pi m and pi p we can calculate, and the delta pi will be effectively given as, in this case, will be given as 0.323 bar, 0.323 bar. Okay. Now, for the first problem, when we do not have any concentration polarization, then Cm and C0 is same. So that's why we calculated delta M like this. And now, so effective pressure will be equal to 2.9 minus 0.3.2, that will be 2.58 bar. Okay. So basically that is the effective pressure, which is the difference between delta M and delta pi, delta P and delta pi. Now next part that they have asked is about when you have a concentration polarization. So in this case, when I have a concentration polarization, then that means that my Cm by C0, that is equal to 5.5, and that will be giving me Cm to be equal to around 0.0825, okay, that will be my Cm value. Now given this Cm, my delta pi will be equal to RT into Cm minus Cp, okay, and if I put the values, I will get the delta pi to be 1.84 atmospheric pressure. 1.84 atmospheric pressure, that will be in my case delta pi. Okay. So if that is my delta pi, then what will be the effective pressure in this case? I will have 4 minus 1.84, and that will be equal to 1.06 atm. So practically in this situation, what you are seeing here is that when I have a concentration polarization, then the effective pressure for me, the effective driving force for me for this pressure filtration, it goes down very rapidly. Okay, it goes down very rapidly, and that's why when we are doing for desalination purpose or any highly concentrated protein solution we are giving, in that case this effective pressure, whatever pressure we are applying, but still we get a huge flux loss or reduction in the flux, because mainly because of this osmotic pressure which is acting in the opposite direction for this case. Okay. So this is about filtration of solutions in a very highly concentrated situation. Okay. Now I will slowly touch upon a gel layer control filtration. Okay. Now what is gel layer control filtration? In my lecture earlier today, I was talking to you about different fouling profile, different fouling regime. Okay. So one was the partial pore blocking. So pores, the walls of the pores are partially blocked, or the contaminant, the particles, they reside on the sides of the pores. Okay, that is partial pore blocking. So now if we have complete pore blocking, so on the membrane surface we will be seeing slowly that a layer of cake or gel will be formed. Okay. So in that case, all the membrane surfaces is fully covered. So nothing of contaminant can come out from this membrane. Okay. So in that case, what we will be seeing here is that my Cp, if we have a complete gel layer control filtration, the permeate concentration in this case will be equal to 0. So no permeate, nothing of contaminant comes out of the permeate, so Cp will be 0. Okay. Now, whenever we have a gel layer contour ultrafiltration, one particular thing we can also notice is that if we plot J on the y-axis and delta P onto the x-axis, that means if we measure the flux at different delta P or effective pressure value, we will see that at initial location it will be increasing. After certain time it will be very flat. Okay. So that means that after a certain value in my delta P, there will be no change in the J value. Okay. So this delta P will be called the limiting flux. This delta P will be called the limiting flux, limiting pressure. Okay. And this J that we get, that will be called the J limiting. Okay, limiting flux. All right. Now also the resistance that is offered by the gel layer, you can understand that whenever a solution is going through the membrane, now if there is a addition along in the gel layer, along with this membrane they have to cross the gel layer also. So the resistance offered by the membrane and the gel layer, that will be added up, okay, in this case. So in this particular specific situation, they are telling you that you have a gel layer controlling ultrafiltration. Specific gel layer resistance is given by some formula, alpha equal to alpha naught delta P to the power 0.3. Now what is specific gel layer resistance? Specific gel layer resistance is basically the resistance provided by unit mass of the membrane, unit mass of the gel layer. Okay. Now let us say that my gel layer has a thickness of L. Okay, gel layer has a thickness of L. And let us say that then per unit area, how much will be the volume? L only, 1 into L per unit area. How much will be the mass? Volume into density, so that will be given by rho g. Okay. So rho g into L, that is practically the mass of the pore, that mass of the gel layer that I have. Now here in this case, I have some porosity of the gel also. The gel layer is porous in nature. So effectively the mass goes down. So in this case, what I will have here, this is the porosity. If epsilon is the porosity, so effectively the mass will go down, and what fraction will be remaining after my void, that much if I multiply, I get the effective mass. Okay. Now effective mass is this much per unit area. Now resistance offered by unit of mass, if that is given by alpha g. Okay. So alpha is basically not alpha g, alpha naught. So alpha naught is basically the resistance offered by unit mass of your gel. So if I multiply all these terms together, I will get alpha, that will be given by this formula. Now this alpha g or whatever we call, this alpha is practically also dependent on, let us call this alpha g or specific gel layer resistance. This will be also given by one formula like a power law type formula, that is given by alpha naught into delta P to the power 0.3, that is given in this problem statement. In the problem statement they are telling you that alpha is 2.56, alpha is equal to 2.56 into 10 to the power 16. So it is given that alpha is equal to alpha naught into delta P to the power 0.3, and the value for alpha naught is given. Fine. Now if we put all the values here, we will see that my Rg will be given in another power law formula. If we combine these two equations, we will get that Rg equal to Rg naught into delta P to the power 1.1. So now Rg is this much. Now Rg naught value I can calculate Rg naught, whatever will be the Rg naught value, this if I combine this, Rg naught will be practically given by this formula, that given by this expression, that Rg naught is equal to alpha naught into 1 minus epsilon g into rho g into L naught. That will be your Rg naught. Now, once this is given, now as I was, so this is about actually the power law relation respected to when we are combining the alpha and your alpha and this, when we are combining these two equations. This equation and this equation, so when I combine, I get this equation. Fine. Now, I was asking you about Darcy's law in the earlier problem statement. Now, Darcy law I can give like this, delta P divided by what? Mu into Rm, that is for pure water filtration, okay, plus Rg so this is having a lot of issues. Rm plus Rg, this is the resistance in series, so that's why we have Rm plus Rg in the denominator. Okay. Now I have a relation between J and delta P. Now if I try to differentiate this delta P and at a particular delta P value, this dJ by d delta P, that value will be equal to 0 for us. So let us find out. So dJ by d delta P value at this particular location, J is not changing with delta P, J is not changing with delta P after this point. So dJ by d delta P, that will be equal to 0, okay, will be equal to 0 at limiting pressure. Okay. So now if I put this Rg value here, so from here I will put the Rg value here, and then if I do this differentiation, I will get the relation between Rm and Rg like this, that Rm is equal to 0.1 into Rg naught into delta P to the power 1.1. Okay, that will be my Rm. Now, so if I try to put these equations into the relations, then I will be getting that delta P value as like this, that delta P limiting will be equal to 10 into Rm by Rg naught to the power 1 over 1.1, and that will be giving you my delta P limiting to be equal to 8876 kPa. Okay. So basically the takeaway message from this situation is that whenever we have a gel layer control filtration, after a certain delta P value, it goes flat, the J does not increase anymore. So if we can get a relation between using the Darcy law between the J and delta P, and then we differentiate and put and we try to find out at which value the dJ by d delta P, that will be equal to 0. In that case, we will be ultimately landing up to that particular delta P value, and that will be 8876 kilopascal for this particular problem statement. Okay. So because of lack of time or because of very much sensitivity of this board, I am not writing too much of in between steps in between. So, but I feel that many of you will be interested to know the in-between steps or the arithmetical steps, the algebraic steps in between. So, for that I will be very happy to discuss after the session that what will be the steps in between. Okay. So, this is how we calculate for any gel layer controlling filtration what will be my delta P value beforehand. Okay. Here I have a problem which is particularly very much well applicable for many desalination plant. Okay. So, desalination plant, what does it does? Basically those places where there is very much lack of potable or drinkable water, we often have to rely on the sea water. But sea water, it has got a very high salinity content. Okay. Normally, usually the salinity content of a sea water is over 30,000 ppm. Okay, milligram per liter, over that. Now, in order to have water to be drinkable, we have to reduce the salinity level below 250 ppm. Okay, or basically even 250 ppm can be tasting a little salty, but in this particular situation we are having a job where I have to reduce the salinity of your water from 30,000 to 250 ppm. Okay. Now this plant, they have told you have to set up a plant and your flow rate throughput should be 1 meter cube per day. Okay. So 1 meter cube per day you are going to produce, and you are given a nanofiltration membrane. Linear permeability is given like this. So all of us know what is linear permeability, right, by now. So linear permeability is the slope of flux versus pressure. Okay. So that is a very basic property of a membrane, and it generally does not change until and unless we have a fouling in our membrane. Okay. Now reflection coefficient is given something, reflection coefficient I will come to it later, and delta pi, a relation of a correlation between empirical correlation that is given, where C is in kg per meter cube, applied pressure difference or delta P, that is 20 atmospheric pressure, polarization modulus. What was the polarization modulus? Cm by C naught, right? So now the hollow fiber module, they have given you a nanofiltration hollow fiber membrane. Okay, now they just want to know that in a module how many of fibers I should pack. So in yesterday, during the tutorial, I was showing you a hollow fiber cartridge. Any of you remember how many of hollow fibers was there in that cartridge? 80, very good. So 80 was there in particular cartridge. Now that was a lab scale setup, okay. But in industrial scale setup, we generally have much more than 80. The diameter of the module is much more than 80. Okay. So in this particular problem, this is a very possible situation in an industrial setup. Let us see how many number of fibers we need to have in a particular module, in this particular module, okay. So now they also have told that each fiber has a diameter of around 670 nanometer, which is very common when we have a industrial scale nanofiber setup, that they are inner diameter, they have around 600 to 700 nanometer. Okay, that is general criteria of this. So now they are asking you how many of hollow fibers do you need? Okay, anybody can tell me how to proceed with this problem statement? So now, okay, now let us have a little discussion over it. So how much of delta P we have been given? 20 atmospheric pressure, right? So 20 atmospheric pressure in kPa, how much is that? Anybody knows how much how many kilopascal in 1 atmospheric pressure? Come on, 101.325 kPa. Okay, so that is the 1 atmospheric pressure, 101.325 kPa. So delta P is 20 atmospheric pressure, so it is practically 2026.5 kPa. Okay, 20 atmospheric pressure. Now, there is a relation for pi is given. Now, effective pressure is what? That we have seen that effective pressure is delta P minus delta pi. Okay. Sometimes some of the solutes which gets filtered through the membrane, they reflect back. It is like the reflection of light. Okay. So that's why sometimes we call the relation like this, that we know this J equal to LP into delta P minus delta pi. This is our famous Darcy's law also, we can say, where this LP we have seen in earlier problem, LP to be expressed in terms of 1 by mu over Rm, 1 by mu into Rm. Okay. So now if the reflection term is coming in picture, then this reflection coefficient of sigma will be multiplied with the pi, with the delta pi. Okay. So now applying this empirical correlation that is given in our problem segment, if we try to calculate the delta pi, then we will see that the value for delta pi is 230.721 kilopascal. That is our delta pi. Now, we know the value of delta P, we know the value of sigma, we have the value for LP, we have the value for delta pi also. So now we can calculate the value for J to be equal to, if we put all the values, it will be, the value for J will be 3.91 into 10 to the power minus 5 to meter cube per meter square second. This will be the value for J for us. Now, this is the flux. This is the flux. We also have the volumetric flow rate. Okay, we also have volumetric flow rate. And how to relate your volumetric flow rate with flux? Flux and volumetric flow rate. Basically, flux is nothing but volumetric flow rate divided by area. Okay, so flux into area I can get to get the volumetric flow rate. So area of any hollow fiber. So hollow fiber, if this is a hollow fiber for you, your water is going through the inner core of the membrane. Now the area is inner diameter into pi dl, inner perimeter into the length of the membrane. Okay. So the length of the membrane is given. So we will be needing this formula, J into A is equal to Q for you. So volumetric flow rate is equal to flux into area for you. Okay. Now, you can imagine a hollow fiber to be a cylinder, like a pipe. Okay. So if I ask you what is the inner perimeter of that pipe, the PVC pipe, inner perimeter of the PVC pipe. If the inner diameter of that PVC pipe is D, okay, pi D will be the perimeter of that particular circle, pi into D into L, the length of that cylinder, will be giving you the area. Okay. So each fiber has pi into D into L, that much of area. So if I try to pack n number of fibers in a particular module, so the total area it will provide will be equal to, this A will be equal to n into pi into D into L. So this D is the inner diameter, L is the length, pi into D is the perimeter into length, that is giving me the area, multiplied by n or the number of fibers, that is giving me the area. And J I already have, Q I already have. So if I solve, if I put the values, I will get by solving them n to be 2825. So 2825. That many number, huge number of hollow fibers I need to pack in a particular module. Okay. Now, what are options? It is very difficult to pack almost 3000 fibers in a module. right? What are the options that you can provide for them? You can divide them into different modules. You can have a parallel connection, like say that you can have, let us say you are able to pack around 400 fibers in a particular module. Okay, your water is flowing, you just try to divide it into 7 parts, 1 2 3 4 5 6 7, 1 2 3 4 5 6 7, 7 parts. Each part has 400, one part has extra 25. So then that will be 700 700 700 700. So like this you will have total two. I told that, so that many number of fibers you can divide them into a parallel connection. So either you can have a parallel connection, but if you provide to do it in a series connection, then again each and every time your CM and CP value will change, and you will have to calculate the number of fibers required more for the kind of situations. Okay, so for this kind of problem, it is usual or it is advisable to try to have a parallel connection to this. Okay, so these are some of the situations that we might face for predicting the flux. There are various models for batch flow filtration or cross flow filtration. There are various models applicable for this, and so I just wanted to give you a brief idea, a very brief idea, that how these calculations are done or how these designs are done in basic chemical engineering subjects. So these are some choices or some equations that we might be applying. So one equation that we have talked about was film theory, another was your Darcy law, another was the how to calculate the gel layer contour ultrafiltration, and then we saw about how to get the reflection coefficient applied in your filtration setup. Okay, so how to calculate the number of fibers in your system. So there are many such possible variations, many such applicable equations in these type of situations, and if I try to explain all of them to you, I will need a one more GIAN course. Okay, so it is just a summary of what I wanted to give you a brief test of how do we do for this kind of situation. Okay, I am sure that if you think you will have a little more questions, but if you have any question now, I'll be very happy to answer. No questions? Okay, so then if you do not have any, you are free to ask later also. It's not that you have to have now. Later also you can ask. So only just a small announcement that tomorrow we will have the evaluation. Okay, so tomorrow we will have the evaluation for whatever topic we have been covering, the basic concepts or basic whatever have been done, not too much details. Try to go through the slides that have been already been shared with you through the Google Drive. Okay, now you have to appear for this test and you will be evaluated. Okay, now you will be given a grade just like a CGPA that you get in your college exam, just like that. This over 90 it is EX grade, over 80 this is A grade, like this. Now one thing you can use for this certificate that you will be getting, you can use this grade is for this is equivalent to a 1 credit course. 1 week GIAN course is equivalent to a 1 credit course. Okay, so if you want to use this certificate for later in your life, say that you want to go for a PhD or any higher studies where 1 credit will be useful or applicable for you, you can use this or cite this. Okay, that is one part, and second part is it is mandatory for everyone to appear for this exam. Okay, and so those whoever has access to laptop, please do or attend this evaluation or quiz over laptop or any other system. If you do not have, just let us know. We will try to arrange a printout or a hard copy for you for the quiz or the evaluation. Okay, quiz will be just MCQ. Okay, MCQ, very basic question, just a multiple choice answer, one choice among four questions. Okay, but you be prepared and go through the slides that we have shared, all the slides till today in the Google Drive by now. So go through those slides, and expected that our offline exams will start around 2 p.m. Okay, or maybe if we have a slight change in schedule, we'll announce it to that. Okay, so but everyone, please ensure online participants will have an option to go for, will have to go through Google form only, but for offline participants you have this option. Okay, so thank you all of you for joining us today, and we will see you tomorrow at 10 a.m. Thank you.